This conference will now be recorded.
Okay, everybody, welcome to session 6 of Black Belt training and already in progress. There you go, Karen.
Thanks, Sadro.
And let's make you beginner. And
all right. There we go. Let me get rid of that. Oh, no. Minimize. There we go.
I have a quick question for the class. Nobody shares their cameras anymore, and I'm curious, is everybody, you know, is everybody finding it easy or difficult to keep up with the class and to, you know, focus on the class? Or are you guys all being pulled different directions and you're trying to like kind of multitask during the class? I can't see anybody's faces, so I can't gauge the crowd, right? I don't know who's here and who's there. And I know that, you know, you guys are doing a great job of participating when I ask questions and stuff like that. But just to start off today, I am curious, you know, how well do you guys feel you're doing as far as being able to really focus and absorb the information, and how well are you able to focus on your projects in the past couple weeks here? So just, you know, who can give me some insight on how you guys are doing?
Honestly, I'm doing pretty good. If people come and ask me for anything, I just tell them to shut it and leave me alone.
You do it in a really kind way, right?
Yes.
Yes.
More or less.
Good. That's good to hear. Anybody else share Lance's optimistic view?
Yeah, it's kind of similar. I am not really disturbed by people bugging me, but sometimes you get caught up doing a little bit of multitasking because you have, you know, multiple screens and you're listening. So I'm a little bit guilty for that.
Yeah, no, that's okay. You know, the punishment will come later, though. I mean, you know, there's going to be a lot of really tough questions for you on the exam, Jeremy. No, just kidding. Yeah, I understand. That's what I worry about. I mean, and this is something you guys are going to run into as you try to make continuous improvement part of your culture. It's really an interesting battle where you're constantly pulled into other directions. You're constantly pulled into tactical problems that need to be solved. And you're going to have to find time to schedule continuous improvement, you know, schedule time to train, schedule time to be trained, schedule time to work on continuous improvement projects in your area, right? And there's just this foundational way of thinking which says, you know, in your brain, this is so important. It has to be as important or more important than all the tactical stuff that's trying to pull me away. And getting that mindset of continuously improving is you know, critical to the mission of our company. And then using that thinking to, you know, portion out some of your day. That's just, it's part of the transformation. And companies that do this really well, you know, they really do block out time for training, continuous improvement, learning, sharing, you know, working on projects, that they make it part of their routine. And yeah, I'm sure you guys are feeling it in this class where you're like, okay, if you guys are in the green belts, you've been in the green belt class for, you know, over a month now, and it's a lot of time. It's a big commitment on your part, and I'm grateful that you're investing that time for yourself and for the company. And the next thing will be, you know, figuring out how do you continue to invest a significant amount of time into it every week after the training's over. All right, sorry for the distraction, Karen. It's just
No, Sadro, it reminds me, it's sad that companies so often are so busy firefighting that they don't have time to figure out how to prevent the fires.
Yep, that's exactly right.
And that's what this is all about. All righty then. So are we at full capacity, or do some people watch the presentation as you've recorded it, Sadro?
No, everybody's pretty much here online.
Alrighty.
Yeah.
Very well. And I must admit, Ryan, I was cleaning up from my garage sale while I was listening in on your presentation, but I was listening intently, I promise.
Well, as long as you were taking a good 5S to the garage, that's always a good thing.
I got that right. All righty, let's go. So we are going to talk about normality and then hypothesis tests and intervals for comparing standard deviations, comparing proportions, and comparing rates. So that's the sort of the end of the what we call the foundations class, and then we're going to move on to experimental design. Did Morton Salt retrieve their books from the post office?
Yes, we did.
Yay! What was involved in that?
Just had to go to, so the post office sometimes doesn't like to deliver packages to us, which is why we ship UPS or FedEx. But they just, for some reason, sometimes they just can't figure out where we're at because we don't necessarily have an address. We're just an exit off of I-80. And that's, so sometimes we just have to go retrieve stuff from them, but.
Fabulous. I'm glad you got your books.
Yeah.
All right, then. We're on page 133. 133. And when sort of traditionally, when we present the t-test or confidence intervals for the mean, your traditional introduction to statistics class, the first thing they tell you to do is do a normality test. Make sure your data is normally distributed. The reality is, although that's part of the theory when you develop a t-test and confidence intervals, there are some analysis methods that really do quite well without normality as long as the process is stable. So just as a kind of get your arms or head around this, when I was exchanging conversation with Dr. Montgomery as I was developing my class, I've written him letters here and there throughout the years because I have so much respect for his knowledge, and he has probably the best experimental design book on the planet in something like its 7th edition. And so I always write him anonymously. He's never met me. I've never met him at a conference or anything like that. And I never wanted to sign as a Minitab instructor because I didn't want him to think that I was a voice of Minitab. I'm just this voice out here. And he's always been incredibly gracious and given me great perspective, even though he has no idea who I am. And for some reason, when I was writing my experimental design class, we got into this conversation and he started expressing sort of his pet peeves about things. And one of his pet peeves was the overemphasis of the principle of normality. And I thought it was quite interesting. It was probably in conjunction with Minitab developing what we called the assistant menu. I pointed to it briefly. In Minitab, we have, it's in 18, it's in 19. You have this thing called the assistant, and the assistant helps walk people through their data analysis. And if we go to hypothesis test, for example, and you want to do a 2-sample T, you see here a 2-sample T, perform a test, help me choose. It shows mu here. So you're going to compare 2 mu's, whereas over here, one way and over, you're going to compare more than 2 mu's. When Minitab was developing the assistant menu, we always understood as statisticians that analysis of averages, so confidence intervals, two sample T, one-way ANOVA, experimental design, even regression, where we have X-Y relationships, we're always taught that you need to prove normality. And I'm always given the feeling, and this is my recollection as a student, that you're given this feeling that normality is a showstopper, that if you don't prove normality, these things don't work, when in fact, it's really sort of the opposite of that. When Minitab developed the assistant menu, well, so we always understood that if you have a big enough sample size, this is the central limit theorem we talked briefly about. If you have a big enough sample size, normality becomes less and less of an issue in these analysis methods. But as a math person, I saw the theorem, and it is a limit theorem, central limit theorem, which means n goes to infinity. And I truly vividly remember thinking, well, this is beautiful, but how big does the sample size have to be for normality not to matter? And if you take some time to look, to use the assistant menu, you'll find that nowhere in the assistant tools does Minitab do a normality test. What they do is tell you what sample size is necessary such that the shape of the distribution doesn't matter. Stability matters, right? Outliers matter, so out of control conditions matter, but the shape of the distribution doesn't matter at some sample size. And they did lots and lots and lots of simulations to determine a minimal sample size where even extreme skewness doesn't impact the results. So I like to set it up like that because I think that's quite different from the way we're usually trained to think about normality. We always think about normality, prove normality, and then you go ahead and do this. So statisticians these days tend to de-emphasize normality, except when it really matters. And we'll talk about that when we move on to the variance tests and analysis around the variance. But as a matter of course, I do a lot of training in the med device industry and pharma, and they have it written into their protocol. You prove normality, then you can go ahead and compare means, or you go ahead and compare multiple means. So here we are. Back up. I have in the notes as we go through the tests, the guidelines that Minitab established with regard to sample size, and you'll find that the sample sizes are rather modest when it comes to the normality condition. We're talking like 15 or 20, I think, is the max sample size that I've seen. This is not a sample size relative to power, so it doesn't necessarily mean you get good power. It simply means that the normality condition is not a big issue. Again, that said, when we jump into a test, you're going to do some graphical analysis to see if you detect any instability, outliers, that sort of thing in your data. That's the first and foremost issue regarding the nature of your data. And typically, as good practice, we then run in and do the normality test. Well, the normality test is a hypothesis test, so it has its own null hypothesis. And that hypothesis is that the population, not your sample, but that the population that a sample came from is normally distributed. So if we're going to do this, here on page 133, we'll go to your DAF data. Oh, yeah. Is Curtis here? Curtis? Curtis was going to be our next fascinating fact presenter. And I put Ryan on the list just because. So, hey, Ryan, do you have anything fascinating or interesting to share with us this morning?
Goodness sake, this is like my third time in a row here. I'm just like the
Oh,
lucky
did
winner.
you already get chosen? I'm sorry, that's why you're not on the list. All right, you're off the hook unless you want to do one.
Well, I'll think of one by break if you want me to go.
How about, I'm gonna eliminate Curtis. And we'll choose calc, random data. Yikes, can I get to it? Crud, my controls are in the way. I'll do that later. All right, let's get to, go to your 2-sample T data. So we already did the 2-sample T. This is the data, hospital A, hospital B ratings. And we already did the 2-sample T test with this data, but we want to illustrate how to do a normality test. Now, if we're going to do a normality test and we've got your data stacked as we have here, we're not trying to show that the stacked data is normal, but that each group is normal. Of course, if they have different means, the stacked data wouldn't be normal. So it's important that we either unstack or, so if we do stat, basic statistics, normality, this requires the data to be unstacked. And for the record, we'd mentioned a few sessions ago that the data menu here in Minitab has a wealth of useful data management tools, and you'll notice unstack is one of them. So we could unstack the rate data and it would put it in multiple columns. But we don't need to do that if we instead, as the book says, go to graph, probability plot, multiple, the graph variable, we double click the rate column. Categorical variable is where we break it into groups. We say hospital. And choose OK. I'm going to do output only so you get a bigger view here. So it put hospital A on this side and hospital B on this side. Minitab in this view puts these confidence intervals around it. When we do a probability plot, this scale, you can see that it is scaled where it's more dense around 50% and becomes more sparse as you approach 100% and as you approach 0%. Picture a normal distribution sort of going like that, where you have high density in the middle and more sparseness near the tails. So this scale is scaled such that here's your data down here, your data scale here. When you plot your data on this scale relative to its percentile position in the sample, if your data is normally distributed, plotted against this scale, your dots will be approximately linear. Ignore the confidence intervals. It's a whole nother story. It doesn't matter whether your dots go outside the confidence intervals. It's a whole nother story. So just ignore those. See the line that goes through your data. That line represents a normal distribution that best fits your data for hospital B, and this line represents a normal distribution for hospital A. And so if your dots are approximately linear in the normality plot, it means just visually, it means your data is approximately normal. to the hypothesis test, we see a p-value. The null hypothesis is that the data is normally distributed. So we hope that our p-value does not go below 0.05. If p is low, reject HO with 95% confidence that it's not normal.
So
And
everybody, this used to trip me up quite a bit, because if you'll remember the null hypothesis for, did my average, did my mean change in my processes always? No, it didn't. And as you're doing your Kaizen event, you're trying to prove that wrong. You're like, oh, I hope my mean changed. I hope I improved my process. Same thing for variability. If you're measuring variability, the null hypothesis is always, no, the variability didn't change. And you're hoping for a low p-value, and you're hoping to prove that the variability did change, that you improved the variability. When it comes to normality testing, it's like the opposite, at least in my brain it is. It's like the default assumption is that the data is normal, right? And you're not trying to prove it wrong. And in a perfect, great, wonderful world, you'd have a high p-value, which means you can't reject the fact that your data is normal. Therefore, that's a good thing. We want to assume our data is normal from the beginning.
that's interesting that you should say that, because people have the same sort of knee-jerk reaction around correlation. We say when we teach correlation, and we're going to sort of do that when we introduce DOE, we teach correlation. The null hypothesis for correlation is that there is no correlation. And for some reason, regularly people will say, why is that? And I tell them, well, Mr. Pearson that invented this test decided that's the way he was going to frame this analysis. So it's quite opposite from what people expect, and why we have those expectations is sort of, I think, intriguing. But there you go. I'm glad you kicked that in there, Cedro. So the null hypothesis is that the population, not the sample, but the population that the sample came from is normal. So you don't want to see a low p-value here. If you do reject normality, you want to give some serious consideration, and this is sort of what the rest of the chapter is about, serious consideration as to why your data failed normality. So we didn't reject normality here, and what I've experienced through years of looking at training and textbooks and stuff like that is we present the normality test, we don't reject normality, and we wipe our hands off and we move on. And the reality is, when you're on the job, it doesn't always work out so nicely. You do have times that you reject normality. And in fact, that was sort of the birth of the non-normal class that we developed at Minitab. Is, wait a minute, a lot of our customers come to us and ask questions. Hey, we failed normality. Now what do I do? Speaking of which, when in the call on Tuesday, when you're talking about reducing the weight of the, is it steel piping? Who was that?
Yes.
So remind me, is it steel?
Ductile iron.
Okay. So Cedro mentioned the word, and I just wanted to kick this in. I wanted to remember to throw this in here somewhere today. Is Cedro questioned the integrity of the steel if the weight is reduced. There's a discipline in Minitab, and I'll tie this into normality very quickly, a discipline in statistics, I should say, called reliability analysis. And reliability analysis is about testing the integrity of products, either under given stress conditions, whether it's forced to failure, or maybe high temperature, low temperature conditions, or cycles to failure, or time to failure. How long will an appliance live? That's what reliability analysis is all about, so that we understand how the integrity of your products under various conditions or time constraints. That's what this world is all about. So if your company does do stress testing, this is the world you would want to be in. And in this world, it is common that time to failure and stress to failure or cycles to failure is not normally distributed. So a big aspect of this data analysis is determining the right analysis for the job, because this kind of analysis actually is sensitive to the condition of normality, unlike comparing averages. So in this world, we say we are 95% confident that 99% of our pipes will endure this sort of stress. It's like a tolerance interval. In fact, some people refer to tolerance intervals as reliability intervals because they use the same kind of analysis and language. 95% confident that 98% of our refrigerators will last at least 10 years. So that's the world we want to be in. If your company does do stress testing or reliability type testing. And again, in that world, it is common that the population is not normally distributed. So choosing the proper distribution for analysis becomes important.
That's a question, Karen. It's probably for Ryan, since he covered the maintenance aspect of the training. Is this a tool used much in maintenance by chance, Ryan?
In maintenance?
Yes.
In what regard?
It's like part of your, your TPM.
Like machinery maintenance?
Yeah.
It certainly could, and it certainly could and probably should be. But I don't think people, well, in general, you think about all these statistical methods that we're using here. In my mind, it's probably one of the lesser known areas and lesser utilized area of statistics. Aerospace uses it heavily, as you would hope, right? Building airplanes and stuff. Automotive uses it heavily. People earn degrees in reliability engineering. But lots of other industries don't use it as much as they could or should to understand the integrity of their products.
Well, and Karen, maybe as we go through the training today, we can try to relate this back to equipment and how we could use this to measure the reliability of the equipment, right? And if you have a bearing on a piece of equipment, right, or you're or if you're doing regular oil testing and you're testing whether you're doing oil analysis to see if your equipment is starting to break down, and you're testing for metals and things like that in your oil, right? How could we use these tools to make our maintenance testing and maintenance schedules more robust?
Exactly. Another aspect of reliability analysis is time between failures, and that's another type of data that is commonly not normally distributed. So that's where you have these two distribution analysis things here. The big aspect of that discipline is determining the right distribution. Not as important when we're doing t-tests, and actually the more modern way of comparing variances doesn't require the normality condition, as we'll see when we get to comparing variances. For the sake of your black belt projects, unless you are embarking on improving reliability, for the sake of black belt projects of assessing mean shifts, and variance reduction, choosing a different distribution other than normal is not an issue. Yeah, good question about maintenance.
Well, this is something where, if you guys are ever, working in your business and you're wondering to yourself, I've got some data here. It feels like this is a place where I could be using some statistics. If you're not solid and comfortable with it, which you won't be, right? I mean, I've been doing this stuff for years and I'm still learning. You can reach out to Karen, right?
Please
You
do.
can use her as a resource. You can call me and Ryan, of course. But when it comes to the deep dive statistical stuff, you can reach out to Karen and she can help you set up a statistical analysis for your specific problem that you're trying to solve. And just remember that as the months and years go by, you have people that you can reach out to help you figure this out. If you're like, hey, how do I use statistics to determine and estimate the next time this piece of equipment is going to fail and how often I should replace these bearings, right? Karen can help you with that, right?
And I mean this so sincerely. I would say that helping people with their statistical situations is my favorite hobby, right up there with gardening and mowing the lawn. And I mean that with, I love them both.
You're a sick person, Karen.
Did you say I'm a Six Sigma person?
No, a sick person. But yes, you're also a Six Sigma person. You're both, and they might be very closely correlated.
Oh, I like cooking too. There you go. But I really, really do enjoy helping people with their data situations, giving them guidance. So please put me on speed dial. All right. So again, so your data doesn't always pass the normality test. So what happens when you fail the normality test? Well, as it says here, the good news is a lot of our analyses, to reiterate, don't really need a normal distribution. What they need is stability, random samples that represent the population. And as it says here, guidelines developed by Minitab in terms of sample size, as long as it's random and stable, is at least 20 for one sample T and a paired T, and at least 15 for only 15 for a two sample T and a NOVA. Most people aren't comfortable with that though, is that they want to pass normality. So what happens if you fail normality? Well, I'm going to think about this in the big picture. There are four general situations. One, you're normal. Two, you're not normal, but you're stable and random. You just happen to follow another case, another shape. We can work with that kind of data from various methods. Three, and this probably sounds like very specific when we talk about general cases, but it's surprising how often this happens. All measurement devices have limited discrimination, right? They cut you off at some decimal place. So the data by virtue of your measurement device is rounded, and depending on the amount of discrimination, you may end up with several data points at a specific value. You can look at it like if you looked at a dot plot, you'd have stacked data, and it even looks stacked in the normality plot. You would see a bunch of values stacked here, a bunch of values stacked here, a bunch of values stacked there. That data will not only fail normality, it will fail any test for another distribution. Even though it could be perfectly random and stable, stacked data doesn't look continuous enough. It doesn't separate itself enough along the number line to look continuous to pass those data tests. We have methods for dealing with that. This is part of what we deal with in a non-normal data class. And it is truly surprisingly common. But the most common reason that data fails normality is not case 2 or case 3. It's because there are special causes that are present. What kind of special causes? Oh, lots of things. shifts and drifts, truncation in the data, people threw out the bad parts. You know, when you're asking people to collect data for you, they either threw out the bad components and only left the ones that were in spec, so the tail gets cut off. Or I was at a company one time, it might have even been one of the Plexus places. The guy said, yeah, we couldn't figure out why this data always had this truncation at the end. And we found out that when people were measuring the data, if the value that they measured at was out of spec, they just keep measuring it. Talk about repeatability. They just keep measuring it until they got a measurement that was in spec. So everything sort of stopped at the lower spec limit. And so it looked like a form of truncation. You might have multiple populations involved. So lots of reasons for what we assign a special cause reason for non-normality.
Well, and Karen, if you remember a couple sessions ago, I always have the question of what about, time to ship data? Because it has a hard stop at 0. We never ship at less than 0. We always ship within our averages, 48 hours after the order was due to ship. And, we always get this perfect bell curve that's cut off on the left side right at 0, right?
Right.
And I always want to know, how do I handle that data? Because it looks normal. It's totally normal, except it's got this hard stop at 0.
Well, I'm glad you brought that up, because when we look at some of the non-normal distributions, several of the non-normal distributions don't extend to plus and minus infinity like the normal one does. They start at 0. The model is one that is, stuck at 0 on the low end of the number line. And so here's your starting point is 0, and they extend to infinity on the other side. One of the popular ones that people hear the name of is the Weibull distribution. Also the log normal distribution. They start at 0. They don't extend beyond 0. So whenever you're analyzing that sort of data, especially with intervals and things, it's important that we understand that these distributions exist and we analyze with those distributions, because they don't predict values below 0. Thanks for putting that one in there, Sadro.
Yeah, I'd be excited to go through some actual data together and see how you would handle it. So, but I know we'll get there.
There you go. So the first thing you want to ask yourself when your data fails the normality test is something that hopefully you've done first. We do the sensibility check, the graphical check first. Do a time series plot. Just do a simple dot plot or histogram to see if it looks like you have multiple populations, outliers, things like that are visually apparent, attributable to some sort of special causes. But if you hadn't done that before and now your data fails normality, reconsider the integrity of the data. So if P is greater than 0.05, we assume normality. We don't worry about it. We move on. If P is less than 0.05 and you've experienced the data is approximately normal before, then you're going to look for special cause variation. You're going to look for lack of measurement discrimination or resolution, the stats that we talked about. If P is less than 0.05 and lacks special cause variation, that's where we get into opportunities. It's good, it lacks special cause variation. We can work with that data and using methods like something called non-parametric methods that don't require normality. We can do a method called transforming, which we'll talk about briefly when we do capability analysis, because Minitab makes it easy to do transformation and capability, because normality is an important condition there, or where we're pointing to we can use analysis tools in the reliability menu, but that takes some work. So this is just an awareness thing on your part. We're not teaching these methods because that's a class in and of itself, these non-normal methods, but awareness part that, one, when your data fails normality, look for special causes. And if no special causes are evident, but situations, as Sadro points out, that are very evident, it never goes below 0. And your goal is to say time to shipment, your goal is to be as low as possible. So your data tends to be near the origin, but can never go below. Then we're going to use other methods. And these are the methods that we might lean on with that. So again, just in awareness from a black belt perspective. So call your local statistician if you run into those situations. Any questions? All right.
I don't have any questions, but I think, when we dive into like playing with the actual data in Minitab, I think that's where we might run into some more questions.
Sure. Yeah, and I'd love to see, as you're developing your black belt projects, I would love to see all your data and, give you my perspective on it. Again, it's truly a favorite hobby of mine. I'd rather do data analysis than read a book. I was never really very good at reading, just which I think enhanced my interest in math. Anyway, so analysis methods that are not, that we say are robust to the normality condition, where normality doesn't really matter all that much, is where we sometimes it gets the most emphasis, are the things we do most often: confidence intervals on means, our t-tests, the paired t-test, ANOVA, which compares multiple means, and it includes analysis of variance that we use for experimental design, or we call DOE, and regression, which is XY relationships, and X bar charts. So X bar charts are a form of a control chart. I think Sadro talked about individual values control charts with you. We're going to talk about charts for plotting means for manufacturing processes. Then methods that are sensitive to the normality conditions. Confidence intervals on the standard deviation. We're 95% confident that our standard deviation is between here and here. That confidence interval and any sort of analysis on standard deviations, like what we call the variance tests, are sensitive to normality. The tolerance intervals that we talked about, which I said are sometimes referred to as reliability intervals because they use the same language. We're 95% confident that 98% of our population behaves in some way. Our capability analysis. If you've heard of CPK, we'll talk about CPK and PPK, CP and PP in the capability portion of our training. And then the individual value charts. So if you've talked about I charts with Sadro as a form of control charting, I charts, because you're plotting the individual values and your control limits are at ±3 standard deviations, that ±3 standard deviations is based on the condition of normality, where 99.73% of your population lies within ±3 standard deviations. That's a fact that applies to the normal distribution, but not to non-normal distributions. So that's why I charts are sensitive to the condition of normality. And there too, when we do the control charts and the capability portion of the training, we will come back around to Minitab makes analysis with non-normal distributions pretty straightforward, both in capability and in the control chart functionality. We'll see here. We do stat, control charts, or quality. You see capability analysis for normal, capability analysis for non-normal. It's right there because it's a big deal. So it's kind of in our face. All right.
So if I select normal there, will it automatically test for normal when I run the test and tell me if I chose the wrong one, or do I have to do a normality test first and then go choose the right capability analysis?
Well, when you do what we call the 6-pack, when you do the 6-pack, it'll show you a normal probability plot, and I'm pretty sure it also gives you a p-value so that you can see immediately whether your data fails normality or not. But
Do you
when
want to walk us, you want to show us, like, you just grab some data and show us what that looks like?
I can, when we do that topic next.
Oh, okay. I was just excited to see it. I can be patient. I've been patient before.
Thank you. All right, so we want to get on to comparing variability. We know that the variance as a statistical term is the square of the standard deviation. So whoever authored the name of these tests called them the 2 variance test and the equal variance test instead of the 2 standard deviation test and multiple standard deviation tests. So it's interesting that this one is used to assess multiple standard deviations, and this one is used to compare 2 standard deviations. It's just the name, but it's used to compare standard deviations. 2 standard deviations, multiple standard deviations. So these are the statistical analysis methods that you will use if you're hoping to prove that you've reduced variability. Reduced variability. So it's not all about the mean. So when I was at Ford Motor Company, this was pre-Six Sigma, if you can believe that there was such a time. Pre-Six Sigma, one of
How
the
did all of us consultants make a living back then, Karen? I don't understand.
teaching TQM.
Oh, total quality management. Yeah, that's right.
Yeah, there you go. Or you were, oh, what the heck is his name? I lost it. Anyway, so
Just so everybody understands, long before the terms Lean and Six Sigma became popular, there was still Duran and Short and Deming and all these brilliant folks. They were teaching the exact same stuff before it got all packaged up and marketed as Lean Six Sigma. It's been around for a very long time.
yeah, it truly is a matter of packaging, and they've done a good job packaging it. I mean, the Six Sigma movement has done more for quality than a lot of the movements have. I mean, there is a wave of just everybody doing experimental design, except it was taught by academics, and you didn't have computers to do the computations for you. So even after you had the training, you couldn't successfully do it because the methodology was too complicated. So speaking of Deming, that was the fella I was going to mention as far as consultants making money. I had the amazing opportunity to go to a Deming seminar when I was at Ford Motor. They must have given a break to co-op students or graduate students or something, because Deming always said, the reason I charged $10,000 for you to be here is so you'd know it was important, or something to that effect. He was a funny guy. So when Deming came to town, Ford Motor always was a big supporter. So that's quite amazing. But sort of on in the same time frame as Dr. Deming was Dr. Junichi Taguchi. And his methodology was using experimental design in somewhat of a simplified manner to achieve robustness. And robustness meant designing manufacturing processes and products that wouldn't demonstrate variability in the face of typical sources of variability. And his big contribution really was the understanding that it's not all about the mean, that variability is a manufacturer's enemy, whether it's in manufacturing or when your product gets to the customer. Variability is a big problem. So his approach to experimental design was to focus on how to design products and manufacturing processes to reduce variation. So we have more on-target performance, less likelihood of producing product out of spec. So he truly was the forerunner of the whole Six Sigma mindset in his focus. So what's Six Sigma all about? The reason it has Six Sigma in the name is the goal to achieve Six Sigma performance, and that is reduce the variability in your distribution such that you have 6 standard deviations between the mean and your specifications. So that's the focal point. That's the objective in a Six Sigma process, and a Six Sigma project is to reduce variability. Well, again, Dr. Taguchi was the forerunner of that mindset. But his approach was through experimental design. Is how do we use experimental design to reduce the variability in performance? Any questions there? All right. So we're back to the data that we used for the paired t-test, which is actual data from a company that manufactures nasal spray dispensers. The company tests the dispensers before and after temperature cycling. The response of interest is plume diameter at a fixed distance. They meet specification as manufactured, but validation testing requires reliability after temperature cycling, where they go extreme hot, extreme cold, and after they've been temperature tested, the team wants to know if the variability has changed. So not just mean.
Hey, Karen, did these guys actually create a nasal sprayer that missed? Because in my experience, a nasal sprayer is always just like a squirt gun. It just shoots a steady stream right up in your nose and destroys your nose. So if they did actually create one, can you tell me who the company is, and I'll go support them with my business.
That's funny. You know, actually, this was like a groundbreaking product that they were developing. I can't remember what ailment that it was used. Oh, it was for people having, hang on. I can't think of the word, but traditionally you'd get an injection when you'd have this attack, and now they could do this aspirator to relieve the response.
So if you're having like an allergic reaction to something, instead of needing an EpiPen, you can take this.
Even more severe than an allergic reaction. It truly is groundbreaking. It was fascinating to work on the project, quite frankly.
Cool.
But I was astonished at the extreme conditions that they had, that the aspirators were exposed to be approved for validation. It was craziness. All righty. So we would think of the null hypothesis as sigma 1, right? Sigma, the population standard deviation, is equal to sigma 2. But because of the way the analysis is done in the confidence intervals, the resultant confidence intervals are framed, Minitab states the null hypothesis as divide sigma 1 by sigma 2 over here, and you get sigma 1 divided by sigma 2 equals 1. So in the greenbelt portion of the class, we looked at a confidence interval for sigma 1 divided by sigma 2. And if that confidence interval did not include 1, we could conclude that the sigmas were not equal. Confidence interval for sigma 1 or sigma 2 did not include 1. We concluded that the sigmas were not equal. And we hoped that if sigma 1 was sigma before and sigma 2 was sigma after, we hoped that that confidence interval, sigma before divided by sigma after, would be entirely above 1, proving that sigma 2 is less than sigma 1. All right, so if we want to do this just to showcase the assistant menu and how to use it, we'll do this analysis in the assistant menu. So we need to find the data that we used for the paired test. So I'm going to go view the data and output. Let's figure out where this is. Not that way, go that way. There we go, paired T. Next to equal variances. And we have sigma before in one column, sigma after in the other column. And we'll do assistant. Oh, by the way, you can do it here, stat, basic stats, 2 variances, so it can be done there. But to showcase what the assistant looks like, we'll do it here, stat. Again, in your book, this is page 142, 141, stat hypothesis tests. Here it calls it 2 sample standard deviations. And if we do it the direction that it's done in the book, we have each sample in its own column. Click there to reveal the columns over here. We're going to do before divided by after. And we're going to choose, is the standard deviation before different from the standard deviation after? And choose OK. Now, in Minitab here, we have that choice in the navigator, but as you'll see here, I go output only to get a bigger view. There are actually multiple windows that come along here. The first, in opposite order, this is looking at the data for integrity. So it says there are no unusual observations, so it's looking for outliers, and it didn't find any. This analysis, so about normality, checking for normality, it says this analysis uses Bonnet's test, which performs well for both normal and non-normal data. Because the sample size are less than 20, the p-value may, so this refers to with sufficiently large samples. Well, what is large? Well, 20 for this test. So it says your sample sizes are not 20, so you might want to consider getting sample sizes of 20 or more if you're going to do this again. But we did detect a difference. So regardless of this business, the sample size was sufficient to detect a difference. So that's giving us a heads up that we got a low p-value here. Sorry. So we scroll back up. This frame is looking for outliers, and it's looking at the power of your test. What is the chance of detecting a difference? So you notice this scale is power. Power is the likelihood of concluding there is a difference. So you don't see that until you click on it like that. Get that nice explanation of power. So we talked about power and sample size. What difference can you detect with your sample sizes of 10? So if one standard deviation was 50%, 52% different than the other, you only have 60% likelihood of detecting it with a sample of size 10. If there is a 66% difference between your sigmas with samples of size 10, now you're up to 90% likelihood or power. But that is a huge sigma difference. So again, that's giving you a heads up for future tests. What sigma difference can you detect with a sample of size 10? And here are your conclusions.
So, and it doesn't matter if my variation is getting bigger or smaller. It's just
Correct.
saying there, we found a difference, right? It doesn't tell you what direction it's going other than whether it's positive or negative, right?
Exactly. This is a ratio. And if the ratio either before over after or after over before is that big, you 66% reduction, you have 90% chance of detecting it. But even you think about reducing your sigma by 50%, that's a huge difference. And yet you only have 60% chance of detecting it with a sample of size 10. So this power table is not a function of what your data looks like or your results. It's simply telling you that with a sample, with samples of size 10, this is the power that you have for detecting these difference values.
And that's just, that's what's interesting is it really doesn't depend on your data at all, right? It's just, you
Only
know,
sample size.
certain sample sizes have a certain power, and that's just how it is, because it's really, it's all normalized out by saying, look, it's comparing the standard deviation of two samples. So no matter what your data looks like, no matter what the units are, whether it's inches, centimeters, picometers, doesn't matter. It's all normalized out because it's a ratio, right?
Right. So we will do the power analysis after we look at these results. So on page 145, we're actually going to do power for variance tests, so you can plan power into your study instead of just use sample size of 10.
Okay, and that percent difference column there, that's really just the ratio of your sigma 1 to your sigma 2, correct? Because if it was a one-to-one relationship, then it'd be 100% or a 1, is that right? Or
Yep. All right. So here are our results, even though we don't have very good power, and this is an important review. When you produce a low p-value, so if I told you you have a 60% chance of detecting important difference, it still means you have a 40% chance that you will. So you might get lucky. We'd prefer to plan strategy into our test than plan on getting lucky. But anytime that you produce a low p-value, power is now a moot point. When we produce a p-value that is less than 0.05, we are 95% confident that the sigmas are different, that the null is false. So even though we've been given a heads up that this wasn't the best testing strategy because in fact it has low power, we got lucky. We successfully detected a sigma difference. So do the standard deviations differ? P is low, reject HO. So sigma 1 is different from sigma 2. And there we go. Now, if we want to see how different the sigmas are, and I don't remember why this isn't in here. This is weird. There are some things, and I like to highlight this too, which is why I don't understand why this isn't in this book. You might want to write this down, is some things, oh, I have it, I'm sorry, on page 143. Page 143, the comparison confidence interval, 143. I printed my slides in 2-ups and I can hardly see them. So comparison confidence. Unfortunately, the assistant menu doesn't do everything, and some very useful things. And that is, as we had with 2 sample T, we had a confidence intervals that compared the mu's with the 2 variance test. We get a confidence interval that compares the sigmas. So back in the mini tab, we're going to go stat, basic statistics, 2 variances, again, page 143. We have each sample in its own column. Sample 1 is before, sample 2 is after, and we choose OK. And we see here there's your p-value that, as we saw in the assistant menu, of 0.046. And consistent with that Bonnet p-value, we have a Bonnet confidence ratio. And we notice that the ratio, and here's where we need to understand how it formed the ratio. Sigma 1 is sigma before, divided by sigma 2 is sigma after. So the standard deviation before divided by after is less than 1. That's too bad, because it means sigma after is higher than sigma before. But as with all confidence intervals, the ratio may be down up at this end of nearly 1, so nearly the same, but it could be that sigma before divided by sigma after is approximately 1/4. So sigma after may be 4 times sigma before. So it's a pretty wide confidence interval, but that's what happens, especially with analyses of the standard deviation with small sample sizes. Okay, this says reject equality. The confidence interval says reject equality because it doesn't include 1, but it's incredibly wide for comparing the sigmas. Again, might be as low as approximately 1/4, might be nearly 1, so nearly identical. So if you're hoping to reduce variability in your black belt project, this is the test you will be using. It occurred to me that with the steel study or the pipe study, that if the goal is to reduce the overall weight, the weight of the pipes in general, and still stay within spec, that may require, you may achieve both goals of shifting the mean down and reducing variability, so you have fewer pipes that are on the high side of the target value. So you may have a double winner there if you can accomplish that. Stay within spec on the low side, but stay below target on the high side.
Can everybody in the class think of an example in your company of where this would be applicable, where you're actually trying to reduce the variation in a process and show that reduction, using a 2 variances test? Who has a good example they could share? Travis, how about you?
I'd say on like the bag weight, for example, that Jacob and I are doing for the Greenbelt stuff, there's you know, we can take the variances of before and after we make the changes and see if they compare. I think that's a pretty straightforward application of it.
Yeah, I think that would be a perfect application. Dustin, do you have an example of where, eliminating variation would be good for your process?
Yeah, I was just thinking, we have on the edge of our sheet, we have a unreinforced, I guess, thickness that we have to meet, where it's just encapsulated, just plastic on plastic, so we don't get stuff in there. And it's supposed to be we're supposed to be a 1/4 inch, but we tend to be kind of on the big end of our spec on that, and a little bit all over the place, and was thinking that if we can get that down to a 1/4 inch instead of the big end of the spec, then that's going to help us and help us be more consistent, just hitting that medium spec instead of our big end of the spec, and kind of going all over the place with that.
Yeah, I think that's a great example. I mean, you could use a capability analysis to determine how often you're within spec, and then as you improve the process, you can use the 2 variances test to determine if you reduce the amount of variation in the process, so the odds of staying within spec increase because your variation has gone down. Okay. Thanks, guys. I appreciate learning more and understanding more about how these are applicable in your industry. I think what will be great is when you guys finish your Greenbelt or Black Belt projects or both, your report outs, if you have these tools in them, will be fantastic, not only because you've made an improvement, but because you can then use your report outs to teach and show other people in your company. Say, hey, this is how you use a control chart. Check out my Greenbelt project, check out my Black Belt project. Here's how you use a capability analysis. Here's how you use a 2 variances test. And once you guys have done this and you have your own examples for from your projects, those can become the training materials for your company, right? You can now take other people through a similar training and say, hey, this is how I did it on my project, and help other people learn the same skill set.
Something that I think speaks very well to the company is when we do capability analysis, although it's sort of traditional anymore to do CPK or PPK, people that doesn't communicate very well. But what Minitab provides when we do that analysis is a projection for percent out of spec. And with that projection for percent out of spec, you can get S double bar, or the almighty dollar, involved there, and compute how you improved percent out of spec on a financial basis. So we'll see where that pops up when we get to capability. That speaks loudly to the company at large. So you can say, well, our project reduced the variability, and as a result of reducing the variability, we reduced the projected percent out of spec by this much, which means we will be saving this much. All right, page 145. So if we know we got this wide interval, so we're not sure if our sigmas are nearly identical or 4 times one another, what sample size should we be using to demonstrate standard deviation differences? So this is on page 145. We're going to do stat, power and sample size, 2 variances to detect these ratios. 75% and 50%. It'd be lovely to think that your distribution after your project is 50% of what it was. But even if it's only 75% of what it was, that's a huge reduction in variability. What sample size is required to get power of 90% or 0.9, power of 95%. Now we get slightly better power or favorable sample sizes if we only test for one-sided, we call it one-sided alternatives. We haven't even mentioned the word the alternative hypothesis, because most of the time the alternative hypothesis, and this is what we conclude, if we reject the null, what can we conclude if reject the null is what is referred to in academic stats as the alternative hypothesis. Most of the time we want to detect a difference either way. So the default is the not equal. But for the sake of your black belt project, you want to conclude that sigma new, or after your project, divided by sigma old, before your project, is less than or equal to 1. So that's the less than. The null hypothesis is sigma before divided by sigma after is equal to 1. We only care that before divided by after is less than. Again, this gives us slightly more favorable sample sizes. So for the sake of your black belt project, we're going to choose the less than alternative. So over to Minitab. Stat, power and sample size for 2 variances. So again, sigma before, sorry, sigma after, sigma new divided by sigma old. If it's 3/4, of course we want to know about it. If it's a half, of course we want to know about it. Sigma new divided by sigma old with 90% power, space 95% power. And under options, we're going to change this from not equal to less than. And when you do this, you have to remember that when you do the analysis, you have to do it framed in this fashion. Sigma new divided by sigma old less than 1. Choose OK and choose OK. So we see, and this is an issue with comparing standard deviations, but after all, if you're measuring bags of salt, this probably isn't all that costly to have a sample size of 155 to get 95% power. To detect a ratio of 3/4. Now, if you were able to reduce your variability to cut it in half, sigma new divided by sigma old is 0.5, that only requires a sample size of 32 to have 95% likelihood of detecting it. But that's a huge sigma reduction. Hey, Cedro.
Hey, Karen.
Have you been on a project where you cut the standard deviation in half?
Absolutely.
All the time, eh?
You know, it's honestly not that hard, at least for a lot of the work that I've done in the past.
Really? That's awesome. I mean, that's very exciting for me to know.
Well, I mean, I'm just thinking of like the hospital that I was just working with this year. You know, they measure how long it takes, for example, to turn around a sample from the lab. So they get a blood sample drawn. How long does it take to bring it back? The variation's all over the place. I mean, sometimes it's fast, sometimes it's slow. It depends on how busy it is and what order it gets put in. And you put a couple of processes in place that say, okay, when a sample comes in, it goes here, it gets labeled, it goes through this flow, it's first in, first out. And you put a process in place, and that variation goes way down pretty quickly. So yeah, I've seen multiple examples of where you can cut the amount of variation in half.
That's truly exciting to know. I suppose because I've worked with the automotive industry and they've been using this methodology amongst industries in general. They've been using this methodology, for such a long time that would be a miracle around here. Trying to double your capability value, it would be a miracle. So, but I guess it's exciting to know that in organizations that are just discovering some of this methodology, that there's, as we say, a lot of opportunity that people don't even realize, using some pretty straightforward processes that are taught in this discipline.
Yeah, I don't know if it's exciting, because it just means there's tons of variation out there and low-hanging fruit, right? It's easy to cut an awful process to double the performance of a terrible process, right? So I don't know if that's good news or not. If it's hard to improve your process, maybe it's because your process is pretty good already. I don't know. Yeah.
So I'd say it's exciting because it demonstrates the power of the methods. I find that when we teach these courses, just what looks like a good idea, and people say, well, that's logical. Well, if it was logical, of course it's logical, it makes sense, but we're not doing it, right? So when you put some pretty straightforward logical processes in place, there's tremendous opportunity to make improvement. So that's pretty exciting. All right. So that's the 2 variance test. And again, that's going to be your sigma after divided by sigma before. And when you do that analysis, if you're planning on these sample sizes for this amount of power, when you do the study, you're going to do stat basic statistics, 2 variances. You're going to instead do sigma after divided by sigma before, and under options, you want the alternative hypothesis to be less than the hypothesized value of 1, all right? Because you have after divided by before, and you want it to be lower. To get this power that's discussed in this table, you're going to do the one-sided test that does less than 1. So bear that in mind if you're planning on these sample sizes.
So have you run that one yet? What happens if you click OK on that? Is it different than when we ran it before?
There is. I'm going to do it both ways. So I have before divided by after. I'll do it 3 ways. We did it, if we do it this way, we see the results. I'm going to do before. This is the direction we did it before, so I'm going to leave that in there, and we're going to leave.
That's the way we did it the first time.
We did it the first time. Okay, so these were the results we got the first time. There's your confidence interval. There are 3 different ways. This is where this is easiest to do in the assistant menu, but you don't get the confidence interval.
This is the confidence interval that they're the same, or that's the hypothesis, and then the ratio is the true ratio of before to after is between 0.24 and 0.98.
Now watch what happens. This is why I recommend doing this in assistant. Watch what happens if I do less than. Now we get a one-sided interval. and we get a p-value that says reject, and it's a lower p-value because again, one-sided tests are slightly more powerful.
So in that upper bound for ratio using Bonnet, we compared before to after.
Mhm.
And if they were identical, if the variation before and after identical, we would get a 1 when we look at our ratio. But that 95% upper bound is 0.865. What does that mean?
That means that sigma before, right? And look at how it's denoted here. Sigma before divided by sigma after is at most 0.865.
That's at most. So that they're definitely different because that's at most. If they were the same or potentially could be the same, that would be a 1 there. It would say the sigma before divided by sigma after is at most a 1, meaning that they could be identical.
And it could be greater than 1. It could be sigma before divided by sigma after, we're 95% confident, is at most 1.7.
But for this example, we're saying we're 95% confident it's at most 0.865, which means we can go to our boss and say there is a difference between our sigmas, right?
Correct.
Okay.
But watch what happens if you choose differently. If you instead, so you really have to think through this when you do one-sided testing. So by and large, I like to stay away from it, but it saves on sample size. So if you can afford the sample size, just do a two-sided test because you get a two-sided interval. Hang on. Sorry. I didn't choose the right one. So now when we do greater than, so now the alternative is sigma before divided by sigma after is greater than 1. That's what we can conclude if we reject. Well, now we're not rejecting and we get a lower bound. We say sigma before divided by sigma after is at least 0.3. So this one-sided testing is very problematic if you don't really put a lot of thought into it. Using the assistant makes it easier because it spells it out. But as we saw, it doesn't give us the confidence interval for understanding how different the sigmas may be. So it's sort of a necessary evil here.
So is it safe to say that we should typically, when we're going into that pop-up window and doing our two variances test, that we should put our after on top and our before below? Because if we consistently put our after data on top and our before data below, then we can always remember that the ratio we're looking for is something smaller than 1, because if it's smaller than 1, we know we have a difference. We know that our variation improved. In other words, we have less variation because our after number up on top in the numerator is smaller than our before data, which is down in the denominator. Would that be a good rule of thumb?
That would be a great rule of thumb, is just do it that way, after divided by before. The alternative is not to mess with it because it just messes with our head. And in here, go to options and put not equal, and we'll see how it increases the sample size. So we're at about 155 for this ratio before, now it requires 187. We're at 32, now it requires 38, not much more. And then we don't have the concern and we get a two-sided interval when we're done.
Okay, so if you can afford that 7 more samples or 30 more samples, then it's a lot better to have 95% power.
Yep, and two-sided intervals when you're done. You don't have to worry about analyzing it incorrectly.
Mm-hmm.
All right, let's get the equal variance test in because it's a short trip. What's that?
Does anybody have any questions? This is important because this is required for both the green belt and the black belt exams or projects, to be able to compare your means and compare your variation, right? So I know we're not done yet, and I know you've got another section to dive into, but does anyone have any questions at this point? If you're totally lost and confused, there's no shame in that. I mean, I get lost and confused all the time, and I've been doing this for a while. So, please speak up and don't be afraid to say, hey, can you go over this, that, or the other one more time? Or, here's my data. How would this apply to my data? Anything like that. Just please, jump in, take advantage of the time that we have now together to get clarity on this before we move on.
And I have to reinforce a sentiment from Cedro that when I talk about the time I feel like we need to have to teach various topics, Cedro in every single conversation has said to me, they need to compare means, two means before and after, and they need to compare two standard deviations. So this is real high priority when it comes to the statistical aspects. So what sample sizes are necessary to compare means and compare standard deviations with high confidence, and then how do we do it? And what are my results mean?
Chad, I know you've got tons of questions, buddy. What are they?
No, I'm good. It's all good.
Good to hear. See that smile on my face? All right, and it is in the book, right? So thank goodness UPS delivered only, what, a week late? Or
Except
2
for-
weeks late? Oh, Lord.
Except for I haven't gotten Lance's book yet. So Lance, I apologize.
Did you receive
Well, I'm
them?
looking forward to when I do get it. So thank you.
Thanks,
Yeah.
Lane. You've been
You should
patient.
Hopefully you've got the digital version, but the actual physical copy, I will drive it to you today. I'll drive you a copy.
Lovely.
Thank you.
All right. So very closely related to the two variance test, and I put this in the category of ANOVA in terms of your black belt project, is you may, in the course of trying to show a mean shift or variation reduction, if you're dealing with data from several sources like cavities or spindles or machines or manufacturing facilities, when things come from several sources, oftentimes one source has a different mean from the other, and being able to shift the mean of cavity 8 toward the means of cavity 1 through 7 is it causes a variation reduction. So this is part of your black belt improvement, is discovering where there are mean differences from multiple sources or where there are variability differences from multiple sources. So although the end game is to show a general mean shift and or a general variation reduction, the means by which you are able to do that is to identify a particular source like a cavity or a spindle or a machine or an operator that produce different results from others. So in that context, you might compare multiple standard deviations using what we call the equal variance test. So page 146, we're now studying conditions conducive to potato rot by injecting potatoes with bacteria that cause rotting and subjecting them to different temperature and oxygen conditions. You use the test for equal variance to test whether the variability in the amount of rot is affected by the changes in temperature and oxygen. So if we look for the data set called equal variances, right there between energy and paired, this structure, the structure of this data collection is actually structured like an experimental design. And we will see how we will be treating the analysis of this in experimental design, which is quite different than what we're going to do here. What we're going to do here is treat each of these conditions, combined conditions, 10 and 2, 10 and 6, 10 and 10, 16 and 2, 16 and 6, 16 and 10, as 6 different conditions. Again, we're going to treat this type of data, the format of this data, quite differently in DOE, and we'll talk about that shortly. But in this case, we're going to do STAT, ANOVA, test for equal variances. And the outcome in the world of DOE is called the response. The response to various factor conditions. And the factors here are temperature. So this factor may influence rot. And oxygen, amount of oxygen may influence rot. So these are the factors in this study. Let me choose OK. So as we see here in this analysis, we treat each of the combination of conditions as a set. And the null is that all variances are equal. The alternative is at least one is different. We come down here and we see a p-value that says do not reject equality, which does not mean we proved equal. It means we did not detect a difference. We see here individual confidence intervals. And no comparison confidence intervals here. So that wasn't a very exciting study, but when you think about the sample sizes that were necessary in our 2 variance test, when we compare more than 2 samples, whether it's means or standard deviations, we compare more than 2 samples, it requires even higher sample sizes to get adequate power. So if we needed sample size of 38 to have 95% confidence that we would detect a sigma ratio of 1/2 when we are comparing only 2. Think of the low power that we're experiencing when we're comparing 6. Here we're comparing 6 different groups, and we only have a sample size of 3 in each group. It's incredibly low powered, incredibly low. We can't compute the power of this test in Minitab. It doesn't have that functionality. But if we do even the 2 variance test with a sample size of 3 to detect those ratios, and we say OK, with a sample size of 3, we only have 1% power to detect a ratio of 3/4 and less than 5% power. If the ratio of your 2 sigmas was 0.5 and you only have a sample size 3, there's only 5% chance that you would produce a low p-value. This test would be a waste of your time. So this test has less power than that because it's comparing more than two groups. A waste of time. So that's the moral of that story.
So Karen, if I was a savvy stats person, could I just say, look, I only want to compare oxygen levels to rot, and I don't care about that other factor, just doing a one factor at a time kind of analysis, would that increase my power?
It could, but sometimes, well, when we analyze it as a DOE, the answer by and large is no, for complicated reason. When we're doing a DOE, when we get to DOE, I'll explain that part because we're talking about means. It makes more sense in the context of means than in standard deviations.
Right, but going back to the explanation earlier that comparing two variances in a two variance test requires a smaller sample size than comparing the difference between three variances, right? So if I'm only comparing two things, then in theory, I should be able to have a smaller sample size to get an equal power. True or not true?
That's true, but the presence of another factor influencing the results complicates that story. But if in fact temperature really isn't doing anything, it wouldn't hurt you to try to analyze it that way. But when we're doing DOE and we're comparing means, you actually have less power when you do one factor at a time analysis.
Okay.
All right. And most of the time when we're doing our DOEs, we're doing a means comparison, not a variation comparison. But again, it wouldn't hurt you to do it that way. So if you wanted to compare two and go basic statistics, two variances, and do both samples in one column, and the samples are the rot and the sample ID is the oxygen, and we say, oh let's say temperature, because there's only two temperatures, right? There are 3 oxygen levels and 2 temperatures, I believe.
Right, so you can't do the oxygen because there's more than 2.
Then, let me do the not equal. And that did not detect the difference. But again, that's still a really small sample size. This is a sad thing about our need to reduce variability in general in industry and service industries. Is it really requires larger sample sizes than people are used to than it does for the mean. But that's a good idea, Cedro. Again, it won't hurt you to do it both ways. It's just that when we look at DOE analysis, we have more power when we incorporate any sources of variability. All right, how about we only have to finish this off and go on to DOE. We're going to do a short segment on proportions and a short segment on rates, and then we'll be off and running on DOE. So I think this is a good time to take a break. Why don't we break until, let's say, 12:10. That'll be a 15-minute break, and then we'll take it through to noon. Oh, that's 10:10. Sorry. Looking at my
Sounds
clock.
good. Perfect, thanks.
This conference will now be recorded.
Nice. I wanted to tell you my little break entertainment when I went upstairs. So our house is built upside down, as we say, which is not very common in Michigan, but quite common in California is where we discovered it. So a lot of times we see birds, we see them from the top, and they look so different when you see them flying from the top than from underneath them. Well, we have a heron that hangs out on those boulders that were behind me when I had lake showing. And I saw him take off. I've never seen him fly. I've never seen his wingspan from the top. It was just beautiful.
How
And for the
fun.
record, herons don't hang in pairs. Swans do, mallards do, geese do, herons don't. So he's always a lone fella out there. It's pretty interesting.
They don't like to hang out in groups then, or couples, I guess. Oh, that's interesting.
Yeah, I looked it up and it's actually a fact. I thought, why have I, for my whole life around the water, always only see herons by themselves? You never see them in pairs. And you always see swans and mallards and geese in pairs. Are Travis and Jacob both online? Travis is, right?
I am as well.
Okay. Yeah, have something interesting to present? Who wants to go first?
I can tell you that sea salt is actually a lot dirtier than regular salt that comes from the nasty Great Salt Lake. It has less impurities.
Sea salt does?
No, our salt.
Really? And why is that?
Just less stuff floating around in the water that is able to get trapped in the crystallization of the salt.
Interesting.
So when they say that, sea salt is healthier, it's actually not.
Interesting. Yeah,
So we've been sold the bill of goods. All the foodies out there are like, oh, you got to use sea salt, but no, we need to be selling the merits of Salt Lake City salt.
there you go. Do they sell it as Salt Lake City salt anywhere?
Well, we don't actually, here at our plant, we don't sell to the little cans you find at the store. We sell as an ingredient for other companies.
Okay.
Like our food grade stuff comes in like 1,000-pound bags or pallets of 50-pound bags.
Wow, that's amazing.
Side question, how do you guys get all the impurities out? What's the process?
Since there's less things floating around in the water, when we bring in our salt and let it concentrate and put it into our pond, there's just the evaporation. As it forms slower, I think it's able to form a better crystal with less impurities.
Is there any processing after the evaporation to further remove impurities, or is that really it?
That's pretty much it.
We wash our salt twice, actually.
Okay, so there is a wash process to, after it's crystallized, you're washing out anything that's not the, sand, dirt, debris, I imagine, whatever happens.
Oh, yeah. Yeah, we actually use the Salt Lake water to wash it, and then we put it in a stockpile. And then when we bring it in for production, we wash it again with well water.
Okay, so the second wash is like a pure water wash.
Yeah.
Well, so fun fact is, how do you wash salt without dissolving it?
Yeah, that's kind of what I'm wondering. I'm like, this whole process doesn't make any sense to me.
That's why we wash it with salt water or with brine water, because then the salt won't dissolve out into that water again.
So if it has a similar salinity, then it's not going to dissolve as the water's washing over it. If it does break down the crystals, it's just a mechanical breakdown, but not an actual dissolving.
Generally, yeah. And then we dry it.
So the water coming out of the well for the second wash, does that have to have the same salinity to not dissolve the salt?
It's not the same. I think the brine concentration to be like totally saturated, it was 26% salinity. And the average salinity of our water that we use to wash, I believe, is around a 9. So it is lower. It does take away a little bit of it, but not as much as you would think.
Interesting.
That's fascinating.
Yeah, super cool.
And our ponds, so fun fact, our ponds are pink right now because of the concentration. So there's certain concentrations and there's certain bacteria that thrives in a certain concentration of salt water. And so if you ever see pictures of the Great Salt Lake or any of our ponds and they're pink, you'll know it's about this time at this concentration that that picture was taken.
Really?
And
You
do
said
those bacteria wash away in the wash, or how do you get rid of the pink?
It's a algae bloom inside of the water that actually, I think it only happens in the south arm. I want to say the north arm has the blue-green algae, which is the toxic one. And it just doesn't form inside the actual crystal. And I don't think that there's enough of it to stick around to be any harm.
Interesting.
Oh, no, there's not.
Cool.
very cool. I was also thinking if any of you are fishermen, if you watch ESPN, they have bass tournaments in the lake that's behind our house. Even in the area that's right behind our house, you'll see hundreds of bass boats out there when they're having bass tournament. So there we go. All right, so watch for Lake St. Clair on ESPN bass tournament.
You won't see any fishing tournament. You won't see any fishing tournaments in the Salt Lake.
Thinking that.
What about that big shrimp tournament we have every year?
We do supply like, I think it's 80 or 90% of the world's brine shrimp.
Really?
And they don't grow in oceans. They only grow in Salt Lake.
Amazing. I'll have to look up brine shrimp. That's fascinating.
Yeah, it wouldn't make for a very fun television show. They're invisible. They're so small. Yeah, that would be a boring fishing show.
All righty, thank you so much. Moving on then, very short chapter, proportions and rates. So all the analysis that we've talked about thus far has been on measured data, which is by far the most desirable. But every once in a while, we collect data under conditions that are pass-fail type data. Even, I was thinking, Cedro, are there any pass-fail sort of data that you have from the hospital?
No, but interestingly enough, we were working with the printing company yesterday, and they are measuring the number of job orders that they have that come in perfect, meaning all the information is accurate or not. So the first measurement is, we had 30 jobs yesterday, 28 of them had the correct information, 2 of them did not. And then the second piece of information is how many defects did each job order have. So if a job order had a defect, in other words, some information was wrong or missing, which pieces of information were wrong or missing and how many. So we have a count of, job orders per day that are defective, and we have a count of defects per job order, or, total defects that we actually found. That was data that we were reviewing just yesterday, so very applicable.
Indeed. So the pass-fail data, it's perfect or it's not. That's where we would apply proportions. And rates are used when you have count data, like just as Cedro mentioned, the number of incomplete or incorrect pieces of information per job order. So that's proportions and rates. Now when your counts, so let's say this company is counting the total number of job orders they receive each day, and those counts don't happen to be hovering around 0. Maybe it's 51, 56, 62, 48, and they're not counting days that they're closed, so they never see zeros. When the counts look like that, you can typically use the continuous data methods for comparing means and variability. But when the counts are low, let's say safety issues within a plant, I saw a comic yesterday, when plants have a posting of number of days without some sort of safety incident. Well, the comic that was in Sunday's paper was Get Fuzzy, and the dog has a thing, a number of days without incident, and it had 0 on it. So this particular day, he spilled ice cream. So anyway, when you have counts that are low, like safety issues within a manufacturing facility, so that you hopefully have a lot of zeros, 0, 0, 0, 1, 0, 0, 0. That's where it's really important that we use the method that we talk about in this chapter for counts, and you want to qualify or improve the rate of safety issues. So that's the nature of these final analysis methods. So proportions to analyze 2-category data, typically pass-fail of some sort, and Poisson rate tests to analyze counts of rare events. So here we go, proportions. So if we want to characterize a population of pass-fail data, so what does your data look like? Pass, 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 fail, 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 pass, 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 fail data. That's what your data looks like. And how do we quantify what's going on in that population? Well, we want to know either the percent that passed, the percent of good parts, or the percent of bad parts, the percent yield or the percent defective. And with a single population, to categorize or summarize that population of pass-fail data, we would do the same thing, use the same methodology as we do to characterize a continuous population, where with a continuous population, there are 2 parameters of interest, the mean of the population and the spread or the standard deviation of the population. We used confidence intervals to answer the question, what is the mean of the population? What is the standard deviation of the population? Well, when it comes to proportions populations, pass-fail, there's really only one parameter or statistic that characterizes that population, and that would be, again, the percent yield or percent defective, which are, the opposite of one another. And we will use confidence intervals to quantify it. So I do a lot of training at Becton Dickinson, known as BD, and they actually have been crazy busy working on the coronavirus situation, testing and vaccines. They work in making products that deal with infectious diseases. So they make medical devices and medical products. They visually inspect their device for cracks. We want to know the likelihood of manufacturing a defective widget. So we go out to the shop floor and we inspect 100 widgets and none are defective. Well, does that mean you're making absolutely 0 defective? Probably not. It's desirable. But we'd like to know the upper limit of what we might be making based on the sample of size 100. So we're going to do this. I'm going to move my tools again. We're going to do stat, basic statistics. This is page 150. 1 proportion. And we're going to do this, summarize data. So if you did have the data, if you did have this, 1 or more samples each in a column, that column would look like just two different words, pass, 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 fail, pass, fail. And if every single widget of 100 passed, you'd have a column that just said pass, 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 that was 100 cells long. But we're going to have what we call summarized data. The event that we're looking for is a failed widget, and that's 0. And the number of trials is 100. That's the sample size. Trials is the word we use in an intro stats course for when you're dealing with what we call binomial data, pass-fail data, 2-category data. We're not going to perform a hypothesis test. All we want is the confidence interval that gives us an idea of what our maximum percent defective might be based on having a sample as good as we could possibly have. So with our 100-piece test, we had 0 failures in the 100-piece study, but with our confidence interval, we say we are 95% confident that percent defective is at most 2.9%. At most 2.9%.
Karen, this makes no sense. We measured 100, we got no defects. How could it possibly know what our percent of defects could be forever and ever?
Because Minitab's smart.
Okay.
Think about, well, it's all a function of sample size, of course. It says this is how the amount of the certainty or uncertainty we have in what that sample is telling us based on the sample size. So think about the purple box. If those purple pieces were labeled pass, 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 but 3% of them out of 1,000, let's say there are 1,000 pieces are in there and 3% of them say fail, it knows the likelihood of producing a sample like this in a population that looks like that.
So even though there's 300 defects in your, well, not 30 defects in your 1,000 piece, puzzle box there, it says the probability of getting 100 in a row that are all good is whatever is X amount. And so therefore, based on that, we know that there could be as much as 3%. Is this the maximum? Is that at most 3% defects?
Yep, at most 3% defects in the box.
Less, I could have 1% defects in my total population.
Exactly. But say we inspected 1,000 of our widgets, because we make lots of widgets, now we're down to 0.3%.
Maximum, 0.3% defects in my total population.
Mm-hmm.
Because that's highly unlikely to get 1,000 pieces in a row with no defects, if there's defects in there.
So on more than one occasion, I've been standing in front of class where the coordinator of the class is also their quality guru, and I unfortunately say something that contradicts what the quality guru has been telling his team, which is unfortunate, but what am I going to do? Facts are the facts, and I'm not standing in class. So here we go. Here's the situation. You can understand this. So I make this big deal about how 30 is not the magic sample size, and we get to this point in class, and they happen to make bottles for the company that manufactures Tide. Okay, Procter & Gamble. And they make heavy plastic bottles for lots of companies, companies that sell the big plastic bottles of oil, and so they do this drop test. So I say, do you deal with pass-fail data? And they jump in, oh yeah. When we come up with a new bottle design, we do a drop test. So we take the Tide bottle and we fill it up with liquid, and we drop it from what might be considered like top shelf height. So we drop it from maybe 6 feet tall or so, and if the bottle doesn't break, then it's a pass. And of course, I have to ask the question, how many do you test? They said, we test 30. This is how far-reaching the sample size of 30 thing is, or ingrained, is appropriately applied. And they said, we test 30, and if none of them break, we consider the design a successful design. So we're going to do a confidence interval for 0 defects out of 30 and see why their company, their customer, wants them to up the number here. Well, because when you pass a product where there are 0 failures in only 30, your percent defective might actually be as high as 9.5% defective. So their customer was saying, you got to test more than 30, and they're going, we don't understand this. What's wrong with 30? Well, that's what's wrong with 30. So that apparently their customer was seeing too many defects in the field where they get plopped off grocery store shelves and explode in the aisle.
So, Karen, you're saying like, I guess I'm trying to wrap my head around this segment. If we wanna, like here we say we make about 1,200 pieces of pipe per day. If we wanna know how often we should sample, then we could use this method.
When you do your sample, what do you do with it? Do you stress test it?
Yeah, yeah.
And so when you stress test it, what is the nature of that testing?
It's really a pass fail.
So you grab a piece of pipe, you bend it, poke it, do something to it, and if it withstands a certain amount of pressure or certain bend or something like that, then it gets a pass. Otherwise, it gets a fail, something like that.
Right.
Yeah, if there's no other way to qualify it other than pass fail, this is the method you would use to understand what percent effective might be in the field.
Yeah, so if you're not doing 100% inspection, you only say, well, we're going to make 1,000 pipes today, but we don't have time to sample and inspect every single one. So we're only going to sample and inspect 30 out of that 1,000. We'll randomly sample them throughout the day. But now, okay, we've got 30 pipes. We pulled them aside, and we want to decide if our run of 1,000 pipes that day is good or not. Well, a sample of 30 says that you could have as many as 9.5% of your pipes are defective, even though your sample of 30 didn't detect any pipes. So that doesn't mean you have 9.5% defects. It means you could have up to that amount, right?
Yeah, that's the amount of uncertainty in this sample size of 30 is. You might be 0, you might be 9.5%. And just as with any confidence interval, and this is hard to talk people into when their sample was 0, but the truth is you might be as high as 9.5%.
Well, and this is a good argument. Oh, sorry, Jeremy, go ahead.
Go ahead, Sejo.
I want Jeremy to go. It's more important that he talks.
Oh no, you're fine. Like I think that kind of clarifies. So I mean, like if you want to get that uncertainty down, in a sense, you would just test more pieces.
Indeed, and we're going to do a sample size right now to see what sample size would be required. Because as we saw here, even with 100, you probably don't want to be passing 3% bad. So, but you might not be at 3%. So what sample size? Oh, that was 0.3. Here's your 3%. So here we go.
So Karen, real quick.
Yeah.
Just so people understand, this is a really good argument for why you should, if you can, collect continuous data as opposed to attribute data or discrete data. In other words, can you measure the thickness of the pipe with a scale, or some sort of a gauge or measurement tool that gives you an exact number that comes in small increments so you have continuous data, as opposed to measuring the thickness of the pipe and saying it passed or it failed. And this really highlights the important difference between those two types of data, because a lot of times people just mark things as pass or fail, and what they're missing out on is, number one, you have to have a lot bigger sample size to detect a defect. Number two, you don't really know how capable your process or how close you are to being out of spec, where if you measure the thickness of the pipe with a gauge, then you can start to measure the small variations in that, and you can know, oh, based on those small variations, what's our probability of going out of spec? How many defects are we going to have? And you can do it with a lot smaller sample size. And that's why we're teaching both methods. And then if and whenever possible, you want to not have pass-fail data. You'd much rather have data that is more descriptive of what's going on.
And sometimes we use we use pass-fail data as a convenience when we're in the course of manufacturing and accept and rejecting lots. You know, we use go, no-go gauges and things like that because that's a convenience. But for your black belt projects, you want to know more about your product. With the pipe, maybe you stress it to varying degrees and you record the stress at which the product has some sort of failure mode. Those stress values would be so much more meaningful than it broke or it didn't break under a fixed stress. It tells you a heck of a lot more about the nature of your product. And as Cedro says, you get more information, way more informative information with far less data. So we're going to go ahead and do sample size. We had a 100-piece test. Our upper estimate we know is about 3%, but the potential percent defective is unacceptable. We don't want 3% of our medical devices to be bad. So we want to determine an adequate sample size to get a more precise estimate, that is a narrower confidence interval. So we know that when we did sample size for continuous data, Minitab asked us for a standard deviation. That's called the planning value, and we have to give Minitab some information to work with in order to give us a sample size here. So we're dealing with a 1 proportion confidence interval. Oh, sorry, up here, sample size for estimation. Sample size for estimation is for confidence intervals. And remember, confidence intervals take your sample statistic and go plus or minus what we call the margin of error. Sample statistic plus or minus the margin of error determines the confidence interval. So the parameter that we want to estimate here with our confidence interval is the proportion. And for the planning value for proportion, the sample size here is a function of what the true population proportion, like the true sigma, of what the true population proportion might be. If you have no idea, you can put 0.5 in because that yields the greatest potential sample size, 0.5. But one would hope that you're not making 50% defective. So if you say, well, at most, we've never made more than 5% defective or 3% defective, you can put that in there. We know from the 100-piece test that we're at most 0.03. So that's what we're going to use here as our planning value. And we want to estimate the sample size. Well, if we say, well, we prefer to be 0, but you're never going to have a confidence interval with an upper bound of 0. So say we were satisfied with a margin of error of 0.03, I apologize, 0.03. And we're satisfied with a max on that confidence interval of 0.01. So that we could say, well, we're 95% confident. If all of our objects passed, we're 95% confident that our percent defective is 0.01. Well, maybe we're not even happy with 0.01. Maybe we want to say 1 in 1,000 instead of 1 in 100. Oh, this is really going to cost you. But I'll put it in there. I didn't do it in the book, but you'll see how ridiculously high these sample sizes get, which is why we way prefer continuous data. Again, it gives us also gives us more information about the nature of the quality of our products. So we're going to go view, output only. So look at those whopping sample sizes. That if we want a confidence interval, a 95% confidence interval with a margin of error of 0.01, 1%, so it would be our sample proportion plus or minus 1%. That requires nearly 1,500. And if we want 1 in 1,000 as our margin of error, that's going to require 115,000 observations. So pass-fail data is really expensive to do testing with.
Just to be clear, that margin of error means I'm looking for a defect rate of 0.03 or 3%, my proportion. That's the defect rate I'm looking for and trying to be under. And to detect that with a margin of error plus or minus 0.01, so that would be a 0.04 or 4% down to a 0.02, 2% proportion. I'd have to measure it 1484 times, or take 1484 samples.
Right.
Right. That's what that
Yeah,
margin
so
of error
if we're at this
proportion.
Yeah, if we're at this max proportion, this is what would be required to get that margin of error, 0.02 to 0.04 exactly. If we're at that max proportion.
And that means if I sample that many, if I sample 1,500, I will be able to detect, I'll be 95% confident that I can detect a defect rate of up to 3%, but not necessarily lower. I can't detect a defect rate of 1%, for example.
Well, if you're at 3%, and we can experiment with it. What's 3% of
I would be able to detect a higher defect rate than 3%. Like if I had 20% actual defects and I sampled 1,500, I'd definitely be able to detect that with 95% confidence. But if my defect rate was like 1% and I sampled 1,500 parts, it's not guaranteeing me a 95% confidence interval or confidence being able to detect that, right? It's 3% or higher, my proportion or higher that I'm able to detect with that sample size.
with the margin, with this margin of error. And actually, as the proportion increases, this sample size increases. As this potential max proportion increases to 50%, the sample size will increase in order to get a margin of error of 0.01.
Yeah, I had mine set at 07 and I would need 2,800 parts.
Yeah, as this increases to 0.5, the sample size will increase to its max. What's 3% of 1,500, anyone?
30.
3 per 100, so 30 per 1,000, so 45? Does that sound right?
Sounds right.
All right, so let's do stat, basic statistics, 1 proportion. And let's say I had 45 defective in 1484. And we want a confidence interval. So notice how this confidence interval, where our sample was approximately 3%, that's at our max. So I now say I am 95% confident that the true proportion is between 0.02 and 0.04. That's our 3% plus or minus your margin of error of 1%. So this is establishing this width of the confidence interval, sample plus or minus 0.01 at the max proportion of 0.03. Now, if we got really lucky and had 0, now the confidence interval is 0.002. But we're planning for the max possible percent defective, which was 0.03, and that was based on our original 100-piece sample confidence interval. But this is illustrating what this is doing for us. And whoever spoke up, I'm sorry I didn't see whose light was on, that said when he tried 7% here, this was sounded like it was nearly double. Who was that?
That was Jeremy.
Okay, thanks, Jeremy. I'm glad you did that. And again, we can do this and see the max size. It maxes out at 0.5 and then it goes down as you progress toward, as you progress back up toward 100%. So if we put 0.5 in here, You're gonna see crazy sample size of 9,700 to get a margin of error of 0.01. So it's really rugged to get tight intervals in high-powered hypothesis tests with pass-fail data. So again, even though we might be using it on the shop floor for convenience, in your black belt project, it's the scientists, the engineers' goal, objective, duty to figure out a way to measure the quality of the product, not just classify it as a pass or fail. Okay, so on page 153, so we did the sample size test. There we go. Here's our 1484. Page 153, this company that was making Tide bottles has increased the sample size. They find that the proposed design is as high as 8% defective. Their customer finds this acceptable, and it's an absolutely true scenario. The customer was a Six Sigma company, and they knew a little bit about this, and that's why they kept coming in on them, which is why then this company X called Minitab in for training. So the engineers redesigned the bottle retest. The first design, they dropped 250 bottles and 11 failed. So far, they've tested 100 of the new design with 0 failures. Can they report with confidence that the new design is better than the old? And as we discussed with the Sigma tests, it's easier to do the one-sided testing when you use the assistant because it gives us more direction. So let's go ahead and do that. So we've got 11 failed and 250 with the original design. So far, they've tested 100 with 0 failures. So we're going to go assistant, hypothesis tests. We're comparing 2 sample percent defective. In the stat menu, it's called 2 proportions. And this is the sample name it anything you want. Bad design. Total number tested, 250. Number of defectives, 11. We have a new design. And so far, we've tested 100. And so far, 0 have failed. We want to know if we need to do more testing or go back to the drawing board. And we only care if the percent defective of the bad design is greater than the percent defective of the new. So again, this is the one-sided testing. And this is why it makes it a lot easier to figure out which direction you want to go. And choose OK. And this tells us the percent defective of the bad design is significantly greater. Oh, isn't that pretty? Significantly greater than the percent defective of the new design. Here, the difference. Bad design minus new design. The difference in our study was 4.4%. When we do the one-sided test, it only gives us a one-sided. It says the lower bound for this difference. So we can say bad minus new is at least 2.7 different, but might be better than that. At least 2.7. Any questions there?
So Karen, I'm still stuck on something you said just before this part here. I think why the proportion is the number of defects divided by the sample. Is that true?
Correct.
So how come a higher proportion, which it seems like that would be a higher number of defects per unit sampled, How come detecting that, I believe you said the higher the proportion, the higher the sample size, it seems like it would be the opposite. It seems like if I have more defects in my pot, it'd be a lot easier to detect them, so I wouldn't need as high of a sample size.
There's more variability in what your samples look like. When you have 50% defective, right, think of all the options for what your sample would look like.
Okay. So
When you have really low variability, your samples consistently look like 0, 0, 0, 0, 0. But when you have 50% defective, think about the wide variety of what your samples might look like. It's the sampling distribution you have to think about.
So the increased number of samples that you need isn't necessarily because it's harder to detect a defect, but it's harder to measure that plus or that margin of error. And
Yes.
so it's really not about the defects, it's about the margin of error. If I want to have a small margin of error as far as what my actual defect rate is, because when there's a high number of defects, there's so many more possible outcomes for my sample of 100, let's say, to know exactly what my actual defect rate is with a small margin of error, I have to dramatically increase my sample size.
Yep. Do you have the picture? Like the mental picture? That's what's going on there.
I think I have the mental picture now.
That's what's going on there. It's the sampling distribution of potential sample outcomes relative to what the truth is.
It was counterintuitive at first, but I think it makes sense now.
Yeah, I do believe it does seem counterintuitive.
Seems like if I have lots of defects, I should be able to take a really small sample and know, hey, this is my defect rate, but that's not true. It's actually harder to know exactly what your defect rate is.
Yep, good question. All righty, and when we say the sampling distribution, again, you think it's the picture. When you think about all our sample averages that we got from the purple population, it's that distribution of sample averages that dictates how wide the confidence interval is. And the same thing goes here. As you could imagine, if you had 50% defective, your sample would be 46%, and Chad's sample would be 56%, and my sample would be 51%. We'd all get different samples, and they vary more from 50 than our samples would vary from, let's say, 3%. Very good. Good question. All right, so on to Poisson rate tests, especially they were actually designed for rare events. You can look up the history on the development of the Poisson rate test when Mr. Poisson developed this for estimating the number of, I don't think was it fatalities from horse kicks in the war, some goofy scenario that this guy developed this test from. But this scenario came up during Fascinating Facts in class, in a master black belt class I was doing at a bottling company years ago. Their fascinating fact was there are more fatalities from vending machine accidents than there are from shark attacks annually. Well, we could look at, any two statistics. We could look at vending machine accidents last year compared to vending machine accidents this year, or shark attacks last year and shark attacks this year. And we know that those sample statistics are going to be different. The question is, are they different enough to say that in general, there is a true difference? So sample statistics are always different. And unfortunately, when we read things or we hear things in the media, we often are getting sample statistics, and we have to be careful. If you're listening to media or reading and you read there is a significant difference, significant doesn't even mean big, as we discussed before. It means usually when they say there's a significant difference, it means they did a hypothesis test, and the hypothesis test was able to detect a difference that we believe is real. That is, it produced a low p-value. but it doesn't mean that there's a big difference. But I was curious, so I said to the class, well, isn't this interesting? We can use this data and do a significance test. So these are the numbers that the person produced for this example. They said, yeah, there are more deaths from vending machine accidents than shark fatalities. And I said, well, this is great. We have a hypothesis test for this. So the unit of study here, and this is when you have count data, you have to define the unit of study. And in this case, it's per year, shark attacks per year. So it says there were 37 known vending machine fatalities between 78 and 95. So that's 17 years. And over the past 10 years, there were a total of 6 recorded shark attack fatalities. So that's what we're going to use. 17 years, there were 37 and 6 in 10. All right. So basic statistics, 2 sample Poisson, 17, 37, 10, and 6. Basic statistics. See, just when they thought fascinating facts was fun, I had to bring it back around to an example. Summarize data. $17 years is the sample size, the unit of study, and we had 37. And for sharks, over 10 years, there were 6 fatalities. And we choose OK. And much like the 2 sample t-test, we get a p-value and a confidence interval for the difference in rates. So this is what we call an exact p-value. This is an approximated p-value, although people tend to believe that if you use normal for something, it must be good. No, exact is better than approximation. This is strictly academic, used in colleges to explain things. So you're always going to look at the exact p-value. And that p-value is definitely less than 0.05. So P is low, reject HO. So we know that the rates are different. How different are they? Well, again, this is per year. Year is our unit of study. The estimated difference is the sample difference. Take 2.17 and subtract 0.6 and you get 1.57. That's the sample difference. I wish it said sample difference, because people think the estimated difference is something that's important. No, the confidence interval is important because the next sample will be different. So the difference is at least 0.7 per year, so almost 1 per year, and possibly as many as 2.5 more vending fatalities per year than shark fatalities. So possibly a little less than 1 per year, possibly as much as 2.4 per year. Again, should look very much like the 2 sample t-test, where lambda here is the rate of occurrence of a fatality. Any questions or comments?
So, not to completely derail us, Karen, but let's talk about some statistics that we hear in the media every day now. So we say, for example, the number of coronavirus cases went up today. Is that true? Because I've heard there's 3 types of people that will lie to you. They're liars, lawyers, and statisticians. And, I know from experience that I can make the data say whatever I want. So when they tell me that the number of corona cases went up or down or whatever, are they telling the truth? Can you give me some real data examples? Like yesterday in Salt Lake, the corona cases we had 36 new corona cases. Well, let's make it a weekly bucket. Last week we only had 1,200 new corona cases, and this week we have 1,700 new corona cases. So it's spiking, it's going through the roof. Is it really, or is that all part of the same population? It's just a different sample in a different day and a different week.
And the thing is that that's funny about this. I don't know if media intentionally, if media doesn't understand statistics well enough to make those kind of statements. They just state the sample statistics. But you could perfectly well test that to see if it's just because last week is going to be different than this week. And there's a 50-50 chance then it's going to be higher or it's going to be lower, right? It's going to be different. And if all things were the same, if nothing had changed in the population in terms of the tendencies, it's still going to be different. It's not going to be exactly the same as last week. And if it's random, again, you're as likely to be above the last week's as you are to be below. So the only way to make it a definitive quote unquote spike or a sense that there's a true increase is to do precisely this test. Week is the unit of study, and you put in your 1,200 from last week and your 1,500 this week, or vice versa. You go Control E, and your unit of study is a week. So your sample size is 1. Sample size is 1. Whoopsie. I don't know if it'll do it with sample size of 1, by the way. And I had 1,200 last week, and I had 1,500 this week. And say okay. And it says that with, and let me reverse it so I don't have negative signs there. So I'm going to go 1,500 this week and 1,200 that week and say okay. So it says, yep, this is enough to believe that there is something different. These are not random sampling differences. That a sample that looks like this is unlikely to come from a population. The sample that looks like this is unlikely to come from the same population as a sample that looks like that. So how many more cases? Well, in the sample we had 300, but on a rate basis, we might only have 200 more per week. We might have as high as 400 a week. If we're talking something more like 150 and 120. Now, can we make the statement? Well, we can say that we had 150 and we had 120, but does that necessarily mean that there's been an increase if this is this week and that's last week? No, we can't say that now because this confidence interval includes 0, which is consistent with p-value that says don't reject HO.
And HO says they're the same.
Right.
Okay, you ready for some real data? I want to know if the number of corona cases in New York is worse than California. So I have both of their confirmed corona cases.
Okay.
And I have both of their populations. Are you ready?
Yep.
So New York has 390,000 confirmed cases. And New York has a population of, where did it go? Of 19 million, or 19.5 million. Let's just call it, let's round it a little bit.
Okay.
Okay. So, and then our second state of comparison is California. They have 190,000 confirmed cases.
Okay.
And the population of California is 39.5 million.
Okay. Well, this would actually be pass-fail data because you either had it or not. So in this case, we'd be back to the binomial. Did you? So we'd be stat, basic statistics, to proportions, summarize data. Number of events in New York is 390,000. out of the number of trials, 19,500,000. And sample 2 was 190,000. And they had 39,500,000. See how that mathematician calls them O's instead of zeros? So much more work to call them zeros. So the sample difference was your 0.02, so 2% in New York minus 0.4% in California gives us a sample difference of 0.15, so 1.5% difference, right? 1.5% difference in the sample. But does that mean we can say that the rate of opportunity here is different in New York? And we can say yes, because the confidence interval for the difference does not include 0. The p-value says reject equality. How different are they? At least 1.5%. Ooh, really tight interval. Why that tight interval?
Well, you got a massive N, right? And a massive number of events, right?
So your interval is incredibly tight.
Yeah, you can confidently go to the news media and say that there's a 1.5% difference between New York and California in your risk of getting corona, or at least in the number of people that have gotten corona in that state per population, per the size.
Yep.
See, if everybody understood stats, then we could make a lot more sense out of all the numbers that are thrown at us every day in the media.
Exactly. And that's why you have to sort of listen with a judgmental ear. You want to listen for that 2 things in any given article that reports statistics. So the statistics can be incredibly accurate, but the way it's reported doesn't give us enough information. What you're looking for is the word significant. And again, significant doesn't necessarily be big. This could say 0.005 and still be significant.
If I'm a sensationalist in the media, I would say there is a significant difference between your chance of getting corona in New York than there is in California. It's much safer. And in reality, it's a 1.5% chance difference.
Exactly. So it doesn't mean significant, doesn't mean big. Significant refers to this, your confidence that it's a real difference.
There is a real difference between New York and California. Not a big difference, but a real difference.
Exactly. And that's another way that things are, and that's not even a false statement to say it's significant. It's actually a more accurate statement for those that know how to interpret what they're saying. When I hear the word significant, you want to think there is a detectable difference with confidence. We detected a true difference. You need to look at the confidence interval to see what that real difference is. Good question. Good example, Cedro. All right. This next chapter is a chapter that we're not going to do in class. I encourage you to do it at your own pace, where we talk about graphs that demonstrate relationships, relational graphs between variables. And so you've got your scatter plot, but this is a multiple scatter plot. And we're going to see a scatter plot when we get into the beginning of the DOE chapter. So some opportunities for data management and different kind of graph depictions. So again, if you're going to be a Minitab user, you might, I believe you will find these in between chapters to be very useful on the job. All right, so on to experimental design with the time we have left. So we're going to introduce modeling using 1x, 1y relationship, because the principles that we use when we fit a 1x, 1y relationship are very similar to when we do experimental design. So with experimental design, Cedro was talking about your multiple x's that that may or may not impact your key performance indicators. So you probably have either on-the-job experience, scientific engineering experience, or historical data that would lead you to various inputs that may impact your outputs. Experimental design is a method that we use to evaluate the relationship between the X's and your Y, wherein we can study multiple X's in the same experiment and separate the influence of each. So that's the beginning of where we're going. We're going to start with something called a full factorial experiment, where we test all combinations of the factors. And the next time we meet, a really important aspect of experimental design is understanding that we don't have to do all combinations. We can do what are called fractional factorial designs. And this is one approach to what we talked about earlier, this sequential testing opportunity, and how very beneficial it is to do your testing like that, both economically and from a learning perspective. So that's where we have to go with experimental design. So when we say single predictor, so regression is the fancy statistical name for fitting an XY relationship, a best fit line like you might do in Excel. But Minitab calls modeling regression. It's not, the world of statistics does, I should say. And when it comes to 1X and 1Y, there are two opportunities in Minitab to fit those relationships. One is under regression, fitted line plot. And we'll see what's in there. That fitted line plot allows us to fit a linear equation, a quadratic equation, or a cubic relationship. And for most normal people, a graph that looks like that would look non-linear because it's curved, but that terminology has more to do with the nature of the math than it does what the model looks like. So that model might be cubic, it might be quadratic. If it's not cubic or quadratic, so maybe it's asymptotic in some fashion, you can use nonlinear regression, which we're not going to talk about in this class. We're going to only talk about linear, quadratic, and cubic models, and not even the latter. So that's where we're at. Generally speaking, once again, we like to look at the nature of the data graphically. So graph, graph, graph before you do your analysis. And when there's one X and one Y, you do a simple scatter plot. Where do we find that? Graph, scatter plot, lets you plot the XY data. And then we go to a place to find the model, the equation that best fits your data. And it usually takes a couple of steps to decide what the best model is. So in step 3, we say we're going to find the best model, improve the model. We usually, unless we see some outliers when we do it graphically, what we have to do to check the integrity of the data is done after we fit the model. So after we believe that we've got a good model and the data is good for fitting that model, we then learn from the model, use the model to get the ideal response, whether it's a target value, a max value, a min value, predict that performance, and then conduct some additional testing to try to demonstrate that your model predicts performance well. And then you decide where to go. So we're going to see this sort of path of modeling as we move from 1X, 1Y into DOE with multiple X's, 1Y. So here we have a silicone sealant manufacturer downloads historical data for one product over 2015. Data on the density, film thickness, and the silicone durometer are collected initially at 3 days, 9 days, 18 days. The goal of the data analysis is to determine if the durometer values at 18 days can be predicted with the 9-day readings. Because if they can use the 9-day readings to predict the 18-day readings with high confidence, then they don't have to do the readings again at 18 days. So we're going to go to first you have to pull up the DOE data file. So here's the DOE data file, and you need to find the simple regression worksheet. And we're going to do stat regression fitted line plot. And we want to know if we can predict the 18 based on the 9-day data.
Excuse me, Karen, where's the simple regression data?
I sent the DOE data Tuesday morning in a separate, it's in a separate data set that I sent in an email on Tuesday morning.
Okay, I still have DAF. Okay, I'll look, I'll pull that up. Thank you.
Thank you. Thanks for asking. So you see here options, linear, quadratic, cubic. And we say, okay. All righty, so here is, I'm gonna get my tools out of the way, get out. There's the model, but we could fit a model to anything. I could go around the class here and ask everybody what your shoe size is and what your IQ is. And I could collect that data, shoe size, IQ, and I could ask Minitab to fit a model. It doesn't know, that doesn't make any sense. It's going to fit a model. The question is this model useful for predicting? Can I use your shoe size to predict your IQ?
I feel like, Karen, we should do this. I think we should do shoe size and height. I want to know if our shoe size is related to our height. I really do. I'm serious.
But I could do.
I want to do it. Let's do it.
Okay, let's do it.
I love regression. I hope through this little section we're doing right now that everybody else on the call will learn to love regression as much as I do. Maybe it's because I'm an engineer, but there's something magical about getting an equation that predicts the future. You know, that equation up there says that, you know, I can plug in any number of days and it will tell me, it will predict an outcome for me. It will predict where I'm going to land, right? Whatever your input is, you can predict the outcome. So if I input my shoe size, it will predict my height, right? If I input the speed at which I cast the pipe, it will predict the hardness of the pipe, or it will predict the number of cracks, right? If I input, you know, the granule size of my salt, it will predict the weight of my 50-pound bag, right? There's so many applications of this, you know, correlation and regression modeling, and through the years in my, you know, in my work as a lean and continuous improvement consultant, I've used regression so many times. It's been really helpful in understanding what inputs are really impacting my output and how confident of that. The R squared, anyway, R squared and R squared adjusted, we got to go into that detail, but it's absolutely awesome.
Well, the important part to look at before we move on to shoe size and height is when I said if I got your shoe size and your IQ, Minitab would give me a model. We need to look further into the analysis to decide whether we can believe that model will do a good job predicting. And the way we do that is we look at our p-value. The p-value, the null hypothesis on this p-value is essentially you cannot use this X as a predictor of Y. You cannot use this X as a predictor of Y. So if you're looking for a prediction equation, you hope you get a low p-value like this, because then we're going to reject you cannot and say, yes, we can. So we're highly confident that we can use this X to predict that Y, because p-value says reject, you cannot. More technically, it says that coefficient should be 0. P says reject that. This does not 0. All right. So this is a believable prediction equation, and that's regardless of the R square and what anybody wants to tell you about R square. The most important outcome in this analysis is the p-value and the confidence intervals that we will get when we make predictions. All right. So there's our fitted line plot. And we will do shoe size and height. There's our fitted line plot. I'm going to do one more thing here. I'm going to do Control E and choose graphs and choose 4 and 1 and choose OK. And under options, I'm going to say display confidence intervals and display prediction interval. Okay, so Control E brought the dialog box back. And if you didn't get it in the first place, it was stat regression, fitted line plot, 18.9, graphs, 4 and 1, options, check, check. And this is basically page 189 and 190. All righty, so what did we get here? We've got the regression analysis again, right? That's the same as I had last time, but now my plot has these intervals on them. The interval that's really tight to the line is a confidence interval, as it says. And this wider interval doesn't get a nice name on it. There we go. Says prediction interval. So, but before we look at that and take this all to heart, we're going to do the data integrity step. And we do this through something called residual plots. Residual plots. So if we go to here, when we fit a line, here's your data, right? Here's your X, here's your Y, and we fit a line for each data value, for each X value, there is a corresponding Y value at each X. Your data value is what we call the observed value. The point on the line at that X is called the fitted value or the model value. The difference between the response itself, the observed value, and the fitted value is called a residual. Now, imagine collecting a lot of data at a single X point. You get this X, Y, you get that Y, you get that Y, you get that Y. One thing we're trying to demonstrate with our residual analysis is if we collected a bunch of data at a given X, we'd see a normal distribution of Ys. And up here, a normal distribution of Ys. But we usually don't have a lot of data at each X. We have, like here, one at this X, one at that X, one at this X, one at that X. So what we do is we analyze the residuals. And if we collapse these residuals, this is a positive residual, this is a negative residual, positive, positive, negative. When we look at the residuals, they should be normally distributed. So we go here, we put the residuals on a normal probability plot, and it's certainly nicely linear. So that means that the residuals are normally distributed. We would also, of course, well, in order for the p-value and the confidence interval to be useful, that p-value and the confidence interval is utilizing the variation in the residuals. So one of the assumptions when we do modeling, and this will be throughout DOE, we'll see those residual plots, is that the variability around the model is approximately the same throughout the model. And that's what we're looking at here. And we do it in what is called the fitted value. These are your Y values. Go back to here. Your Y values. Look at this equation here. You see your Y values are 185 to about 2.1. So here's your 185 down here to a little bit above 2.1. So we plot the residuals in this order. Notice that you think about the 0 line is where your line is, your actual model is, and we see that there's a nice sort of random cloud here. About half the data above the line, half the data below the line, randomly scattered around the line from the low Y value to the high Y value. So we want to see a random variability around 0 with approximate constant variability. That implies that, if we go back up here, as we see in this picture, the variability around the model is approximately the same throughout the range of your X's. So that's what we're looking for there. If you doesn't look normal, what you'd see is a curve that's like a snake around the normal line. But what the histogram is useful for is when it doesn't look normal, you're going to look down here to see if that variability around the thing looks right skewed or possibly left skewed like that. And that'll help you understand what model you might use instead of the normal model. But vast majority of time, it's approximately normal. This is the order of data collection. And we'd like to see that the order of across the time that you collected your data, the data was approximately random and had equal variability. So those are our checkpoints. One more thing, and then we'll do shoe size and height, because I know we're dying to know here, is the difference between the confidence interval, which is the tight one, and the prediction interval. And something that's interesting about this, or kind of nicely illustrative, I think that it tells the story for the difference between the confidence interval and the prediction interval quite well. Usually it's not this glaring, but we have a sample size of 1,809. So the confidence interval, notice how tight it is to the model, is you say you're 95% confident that the true model is within the confidence interval. The confidence interval is predicting for the mean of the distribution of the variation around the model, the mean of the distribution around the model. Whereas the prediction interval, the thing called PI here, the wide interval, is sort of an odd interval. It goes like this. If I went back and I did one test at 9 days at 2, and then I measured it, same element at 18, one test, I am 95% confident that that one data point would be within my prediction interval. So I'm 95% confident that the model itself, which is predicting for the mean performance across this variability, the model itself is in the confidence interval, the mean at 2, whereas a single test at 2, I'm 95% confident will fall in the prediction interval. So let's turn off your mutes and let's get some shoe sizes. Cedro?
10.5.
Do them first come, first serve, so we'll be a couple hours.
And your height?
5'10".
5'10". We're gonna go.
We probably want to do that in inches.
Exactly. So we're gonna go 70 inches, right?
Yep.
Okay. I am an 8.5. And I'm 5'6", so 66.
Is that a men's size or women's size though?
Oh, you're right. Wonder what I'd be in a men's size.
Isn't it 2 sizes different or something like that?
Let's pretend. All right. Next.
This is
Yep.
Lance. I'm a 12.5 and height is 75.75.
Men to women shoe sizes is a size and a half. It's 1.5.
Okay, so make this a 7. All right, next.
Jeremy, I am 11 and I'm at 74 inches.
Lovely.
10.5 and 71.
10.5 and 71. Next.
11 and 72.
10.5, 72.
And 71.
There's still 11 on the call. There were
9 and 69.
9 and 69.
14 and 77.
Wow, make them tall out there.
9 and 66.
9 and 66. Is that everybody? All right, let's regress. Stat, regression, fitted line plot. Have you done this one before, Cedro?
I have.
Funny. So F3 clears the dialog box. So I want to know if we can predict your height based on your shoe size. I always want to do the height and the shoe size and IQ, but I don't know my IQ.
Yeah, I don't know either.
I don't think I want to know.
Tell the truth anyway, so.
What's that?
Then I wouldn't tell the truth anyway, so.
So we'll go to graphics and do 4 and 1. We'll go to options and get those confidence intervals and prediction intervals. And choose OK. And choose OK. So the first question is am I confident that I can use shoe size to predict your height? Is there a true relationship? And what tells you that is the p-value. The null hypothesis is you cannot use shoe size to predict height. P says reject HO. So we are confident that there is a true relationship between shoe size and height. We're going to check the data integrity before we go any further. We come down here, approximately normal. Remind you of a tool that we looked at very briefly, this brush thing. I can do like this and figure out which point that was. If I had placed our names in there, I could use this thing, set ID variables, to demonstrate the names. Just wanted to remind you of that tool. Mess around with it back at your desk. We look across the fitted values. We're hoping to see randomly scattered around 0 with approximate common variability across, and it's really hard to detect that with smaller data sets. Since this is approximately linear, we don't need the histogram, although if anything, it looks a little bit left skewed. And time observation order is time, and that doesn't mean anything here because we are randomly This is manufacturing order typically, or measurement order. So we're comfortable with the data integrity. So now we come up here. So the green interval, the inner interval, says we're 95% confident that the model, the relationship between shoe size and height is somewhere in this interval. Mind you, the intercept could be a little bit different. That would push the line up and down. And the slope could be a little bit different, which would make the line go either steeper slope or more shallow slope. That's why it fans out at the ends to account for varying slope. So think about tilting this either to a lower slope, in which case this end goes up, or a higher slope, in which case this end goes down. Again, that's why you have the fanning on the confidence intervals. We're 95% confident that the true model between shoe size and height is somewhere in this interval. Now, if I want to predict a height, my predicted average height for a shoe size of 10, predicted average height is the fitted value, but you can think about that fitted value like an X bar. Because of the uncertainty in who the model truly is, that's explained by the confidence interval, we can say that I am 95% confident that if a person has a shoe size of 10, the average height will be somewhere between there and there. And in fact, let's do that. In this dialog box, there's no place to do prediction. So in order to do prediction in regression, we have to go stat, regression, regression, fit regression model. Now you see hidden buried in here is predict, but we can't get to it until we fit the model in this menu. Fit regression model. The response is height. The predictor is shoe size. And we'll say okay. So of course we get the same model, but now that we've done that in the regression menu, we can now get to predict. And let's say I want to predict for a shoe size of 10. And say okay. So here's the confidence interval. Here's how I say this. We are 95% confident that the average height of a person with a shoe size of 10 is between 69.5 and 71.3. The average height between 69.5 and 71.3. Now, if I go out.
Just to be clear, Karen, I could look at that regression equation and plug in, on my own in my calculator, any number where it says shoe size. So I could take 52.46 plus 1.798 times and then put in any number there for shoe size 10, 10.5, 11, 11.5, 12, and calculate that height by hand, which would be the same number as that fit down below, right?
Right. But we know that you want to think about this model as being like a sample statistic. The next sample that we would get would be slightly different, so we'd get a slightly different model. So we think about the fitted value like an X bar at that, like a Y bar at that X. But the true average, the mu of Y at shoe size equal 10. So again, this number came by putting 10 in there, multiplying that, adding that to get the fit. But the true average height of a person wearing a shoe size of 10 is at least 69.5 and at most 71.3. Notice the prediction interval is wider. The prediction interval is trying to capture one value. So I go out on the street right now and I ask all my neighbors, what's your shoe size? And I find somebody whose shoe size is 10. I am 95% confident that that single person will be at least 67 inches, 67.4 inches, and at most 73.4 inches. A single person that I find that has a shoe size of 10. Any questions there?
So Karen, I know. Oh, go ahead.
No, go ahead.
Did you have a question, Dustin?
Yeah, I was gonna, so the confidence interval on that is you're saying that your average, if you were to go out and talk to a bunch of people with size 10 shoes, their average would be between that, but the single person would be between your predictive, correct?
Exactly. So
Okay.
I personally think that the prediction interval is sort of one of the lingering old-fashioned statistical things. It's in every textbook, everywhere you read about modeling, you'll see prediction interval, but it's incredibly academic. I think that in manufacturing and in service industries, when we do this kind of modeling, we want to be able to say, I'm 95% confident that 98% of the product that we produce at 10 is in this interval, but that's not what this interval is. It's if I go out and I manufacture at 10, one item, I am 95% confident that that one item manufactured at 10 will fall in the prediction interval. It's very academic, which means not useful on the job. That's a translation. What we really need on these models, and it just astounds me that Minitab hasn't done it, are tolerance intervals. So you'd see a 95, 98 tolerance interval. So you could say I'm 95% confident that 98% of the product manufactured at this setting will be in my interval, and then you'd compare that to your specs. Any questions there?
I guess the only thing I have is you really don't use the R squared much, and I guess why?
Because, and I have to see if this slide is in here. It's got to be in here. I don't know where it's at.
Don't break my heart, Karen, because I love I love the R squared. So don't break my heart here.
I'm probably going to.
Oh.
I have a slide in here that somebody made for me in class with a couple of guys from the same company when I did in a public training one time. It's got Batman and Robin. And I'll find it. But I'm going to quote a statistician that owns a software company named StatEase that makes a wonderful design of experiments software. And he has an article that he wrote a long time ago. And the title of his article is R Square, the Big Fat Idiot. So people pay too much attention to R square. In that, what you really need in order to understand the nature of your model, you need first the p-value to tell you whether we can trust the model, right? If I had 2 data points, imagine I had 2 data points. I got a data point here at 8. Let's just say I have this one and this one, that one and that one, and I fit a model to that, right? It's going to be a perfect fit, and when I have a perfect fit, my R square is 100%. How much would you trust that model? Anybody? 2 data points.
I would trust it 100% because my R squared is 100%, Karen.
Would you really? This is a sensibility question, not an R-square question.
I wouldn't, just because of your sample
Only
size.
2 data points, but you have a R-square is 100%. Well, let's look at this. This R-square is only 68. Do you trust this model? Less than you trust this model? Which model do you trust more? This one that has R-square equals 68 or this one that has R-square equals 88?
One that
Just
has
look at-
68.
Yeah, it has a heck of a lot more data. You can clearly see that, and check out the confidence interval around the model. It's telling you you're highly confident in the nature of that model for predicting average performance. But there happens to be a lot of variability that around the model. That's what this is a measure of. Variability around the model, but that's the nature of this process. And in fact, in this article written by the Statties man, which by the way, their DOE newsletter is always credibly informative and entertaining. They're very funny, like this one. But it was an FAQ in his article that somebody said, what type of R-square should I see in designed experiments in manufacturing? And what he says is, I'm quoting something like, kind of quoting, he says, I have done thousands of experimental designs over my career, and it is not uncommon to see R-square values 50% or less because of the inherent variability in the manufacturing process. But people that don't understand R-square well enough would look at an R-square value of 50% and sort of give away the nature of the model, where this confidence interval is telling you, you can really trust this model because it's really tight interval. You can really trust this model for predicting averages, really tight, as we saw. Whereas this confidence interval says this model is a little farther off, even though it has 88% R-square. We have less faith in our ability to predict with this model because its confidence intervals are wider.
So Karen, let me run something by you. When I have looked at confidence intervals in the past, and I don't remember exactly where I learned or was taught this, but the way I understood it was my R squared or R squared adjusted explains 88% of the variation I see in my Y. In other words, this model with this confidence interval in between those green lines explains 88% of the variation that I see in my Y. That additional 12% of variation that I see in my Y is coming from other sources than my shoe size, for example, coming from other things. But there's 88% of my model explains 88% of the variation. How close is that statement to being true?
Oh, it's true, but it's not the most important aspects of assessing the usefulness of the model. The first really important part is the p-value. It tells us whether we believe there is a relationship. And the second is, when I want to use this model to make predictions, how good do I feel about those predictions?
Right, but in my mind, right, if I look at the two examples you've got here, the green lines of the confidence intervals are very far apart in the example with a low sample size, the shoe size and height. They're very tight on the example that has a high sample size. And in both cases, if I understand the separation of those green lines, my confidence intervals, if I understand that is, the model is explaining that we're confident that it's within that range, right? Then my R squared makes a ton of sense to me because I'm saying, well, this model with this confidence interval explains 68% of the variation that I see, right? And that the fact that I'm looking at my confidence interval and those green dashed lines, it's putting into context the sample size, and therefore the amount of confidence that I have because it's based on the sample size and so on, right?
So when we look at this 68%, right, ignore the X's and think about the variability in the Y. So just think about the distribution of Y's here, right? So you've got your variability in Y. Some of that variability in Y is due to the XY relationship. And the rest of the variability in Y is due to random variation.
Or
So
some other factor that we haven't taken into account.
Well, whatever this is, whatever caused this random variation around the model, whatever caused this variation, whether it's random or not, and oftentimes it is. I mean, the residual plots tell us that it looks like it's doing what it's supposed to be doing. It follows a normal distribution, and it's randomly distributed around the model. So based on residuals, I'm going to guess this is random variation. So you've got your random variation around the model, and you've got the variation along the model. How much variation and why would we expect if it did exactly what the model tells us? That random variation plus the variation along the model is equal to the total variation in Y. And so we say that R square is the percent of variation, total variation in Y that is explained by the model itself. But in this case, we have great faith in who that model is because of the tight confidence interval, its ability to predict the average, but it's not going to predict individual performance as well because you have a lot of inherent variability. Which why this 68.
Yeah, which is why it's only 68%. The model is going to explain 68% of what you see in your Y, and there's going to be another, 32% that's going to be explained by other random variation that's you see.
Right.
Well, you're making me happy, I think, because this is what I've understood and explained for many, many years now, but I still like the R squared because I think it does explain it. In my mind, it clicks for me. It makes sense.
Well, unfortunately, people discount the value of the model. This is a problem with it, is that people discount the value of the model based on the R square. And R square is not an indicator of your trust in the model.
Right, the model's right based on your p-value, no matter what your R squared is. Your R squared just explains how much variation the model explains.
Right. So that's the nature of that beast. Its p-values and confidence intervals tell you how valuable the model is for predicting average behavior and for predicting single behavior.
Not to jump too far ahead, but when we start using our Statipulse in the next session, if you're using the pullback distance to measure how far the ball launches, everybody hopefully has their Statipulse. You know what I'm talking about. You pull the ball back so far and you measure how far the ball launches. That will explain some amount or some percentage of the variation we see in the Y and how far the ball goes. But then when you add, and you'll get an R squared value, but then when you add in the stopping point for the catapult, or you enter in the ball type, the type of ball that you're using, those will make the model, the regression equation, more robust, and it will explain more of the variation when you have all three of those factors involved. And then your R squared value, we'll see when we do the Statipulse, will actually go up because we're now explaining more of what we see in our Y because we have more factors that are contributing to the variation that we're taking into account. So anyway, I'm excited for the Statipulse. It's going to be so fun.
Yeah, I was really hoping that we'd get a little bit of DOE in today so that we could do that initial experiment, but so
I think we did. I think what we covered today was very much DOE. It's awesome.
So yeah, where we're going from here with experimental design is you will be varying the balls and varying the launch configurations and then measuring the distance. And so that's the nature of the experimental design, is you decide what range of values that you want to set for each of, there are 3 rubber bands, so you can use 1 rubber band or a maximum of 3 rubber bands. And again, varying pull conditions and 2 different balls, all of those are factors. And the DOE will tell you what combinations you ought to be testing, so we can get away with a minimal amount of testing and still be able to get a model that utilizes all of the factors that you varied in the experiment. So we can separate the impact of each of the factors because we did the experiment as a planned or designed experiment. So, yep, that's where we're going with the Statapult. So what we're going to do is you're going to test varying conditions. And as we mentioned last time, you're going to need a spotter of sorts to see where the ball lands. That's the distance it goes. And after you complete the experiment, you're going to use that model to predict where the ball should land for given conditions, and then demonstrate the usefulness of the model by putting a receptacle at varying distances and setting the factors at settings, levels that would give you the desired distance. And if you haven't seen the video at the XPult site, I would encourage you to see them. They're just having a ball with the thing. It's pretty funny. So there we go. We're 2:03. Any closing remarks, Cedro?
No, that's it. I was just going to send people a link. If you Google XPult Catapult video, you'll pull up the results here, which is, you'll see several videos that they posted. But it's a lot of fun, and it's a great way to learn some stats with some hands-on training. So.
Well, I hope that the models predict as well as the videos make it look.
Yeah, you should be able to stick a cup on your table, and you should be able to randomly place your cup at a certain distance and then control your settings to land it in the cup first try. If the DOE experiment, if you get the right regression equation, you should be able to nail your ball in the cup first try, which is a whole lot of fun when you master it. So get those Statapults out, maybe play around with them between now and the next time we meet, which will be next Tuesday. And don't forget to work on your projects. Again, we are going to be setting up one-on-ones for next week to review your projects and see where you guys are at and help you make progress there as well. So Brian and I will reach out and set up times for that as well. Any other questions before we wrap up, guys?
Guess that means no, huh?
That means no. Have an awesome day, guys. Wear your face masks.
Thank you.
You're
Thanks,
welcome.
Lance.
Have a nice weekend.
See you, Travis.
Thank you.
You bet, Dustin. See ya.